Now
Oh,
it
this
is
is it.
happening.
Yeah,
Okay.
it's live
All
now.
right, all
So
right.
you
Okay.
just
I thought
stop
this is where I
sharing.
had two different space gigs. So okay,
No,
that's
no,
cool.
no. See, procedure is very simple.
Okay, cool.
We
Done,
are
done,
live
done.
now. Okay.
It's like
Amritanshu, can you just check?
Okay, so let me see. Just wait a
Yeah,
second,
we
sir.
should be live now.
yeah, we are live.
Yes,
Hope it's
it's
taken.
live, sir. It's live, sir.
Okay, I'll stop sharing my screen then. Okay, so shall we start?
Yes.
Yes, I'm ready.
Good afternoon, India. This is Amritanshu Vajpayee. I welcome you all to the third day of the National Technology Day celebrations 2021 on the occasion of the event of Advanced Technologies and Applications in Engineering on behalf of the organizers, Indian Space Industries Exhibitors. As we all know, for the past 2 days, we have been taking out and providing you with the lectures from the esteemed and distinguished guests from different institutions of repute. So, on the same trending line, today we have again for you three special lectures from three distinguished guests from different institutions, beginning with the innovations in advanced manufacturing technologies by Professor C.S. Kumar from IIT Kharagpur. We shall then be taking you to the polymer composites and understanding of high-end applications by Dr. R.M.B.G.K. Rao from NAL Bengaluru. Also, the final lecture shall be given by the applications of advanced materials in spacecrafts and aircrafts by Dr. Gajveer Singh from ISRO Bengaluru. So this is the schedule for the day, and I wholeheartedly welcome you all to the live streaming platform of YouTube. I also welcome on behalf of all the knowledge partners of Indian Space Industries exhibitors, the first speaker of the day, Professor C.S. Kumar from IIT Kharagpur. And also we have a very special guest amongst us, Dr. Nand Kumar, a scientist with specialization in remote sensing. Welcome, Nand Kumar, sir, to this platform of ISIE. So now with these words, and welcoming all the participants and all the guests who are here on the different platforms, either they are joining through the YouTube shared links, streaming links, or the internal meetings of ISIE. We really request you, if within the course of the talk by the distinguished speakers, honorable speakers, you have got any queries, do post them into the chat boxes of the YouTube, as well as those present in the internal meeting, they can put their queries directly to the honorable speaker. Our technical team shall constantly be monitoring them, and we shall be putting them on to the speaker for your proper redressal of the queries. With these words, I welcome Shri Chintamani Pai sir from Space Geeks, one of the knowledge partners of ISIE, to formally take us to the session of the day. Over to Chintamani sir. Welcome, sir.
Yeah, please switch on your mic. Unmute your mic. Chintamani, please unmute your mic. Yeah.
Am I audible now? Yeah.
Yes.
Yeah. Good afternoon, everyone. This is Chintamani Pai. I am a co-founder of Space Geeks, a young startup in space, and we are happy to be a part of this event with Mathur sir. And he has been really encouraging to organize these events and to create awareness about space. And uh, it's I hope that all of you are enjoying such beautiful talks, giving you insights into advanced technologies. And it's my pleasure to briefly introduce today's speaker. I welcome Professor C.S. Kumar. He's from Mechanical Engineering Department of IIT Kharagpur, and today he will be taking us to the journey of innovations in advanced manufacturing technologies, and which will include uh, the aspects of additive manufacturing and how to come up with new innovative approaches in the field of additive manufacturing. Good afternoon, sir. Uh, it is over to you now.
Thank you, Chintamani, for the quick and short introduction. It is nice to be associated with this event, the Space Geeks. And I would also like to thank Dr. Mathur, who invited me for this talk from ISRO. It's indeed a pleasure to interact with him, and his requests will always touch those parts of my activities that I try to see what best I can bring forward to the audience here had planned for. Also, I welcome Dr. Nandakumar for his interest in this. I have briefly prepared this talk on additive manufacturing as an advanced manufacturing concept. There are many things in advanced manufacturing that are possible, but I am limiting myself to additive manufacturing itself. Now, before I start, while I'm getting ready for the presentation, somehow it is not allowing me to share the screen. Can you please give me the permission to do so?
Hari, can you allow multiple participants option for sharing?
Done. I have permitted it.
Yeah, thank you. I'm now getting this. So now let me, yeah. Screen is probably a little bit cluttered. There's a lot of slides I've prepared for a 1 hour talk. Okay. Yeah. So this is the topic. I hope you're getting to see my first slide, the title slide.
Yes, sir.
Yeah.
It's visible.
I called it ISRO Technology Day. It's actually the National Technology Day of ISRO. So I perhaps misuse the term. Let me introduce myself briefly. I am Professor C.S. Kumar from the Mechanical Engineering Department of IIT Kharagpur. I am a graduate of this institute in the year 1987. After my schooling in 83, my first, I can say, as like any young geeks in this one was always aerospace industry, and I literally fought with my dad that I wanted to join aerospace, but then manufacturing was just upcoming, and we were looking at aspects of doing manufacturing engineering, advanced manufacturing in mechanical. So that was the undergraduate program I joined as a BTech student way back in 1983. Providence took me through it. And then after several years of work in basic manufacturing engineering, manufacturing science and engineering, where IIT Kharagpur happens to be the first institute which introduced this program in the undergraduate level. And thereafter, I went into robotics and automation. And about 12, 13 years ago, I got into additive manufacturing, wherein due to an assignment that I had been given to work with, and that's I will talk about with my experiences in that. I'm also happy to have people from ISRO like Dr. Nandakumar and Dr. Mathur. In the recent 3-4 years, I've been interacting with this SAC Ahmedabad group on another aspect of technology of ISRO, that is the navigational technology using NAVIC. And in that we had tall plans. We planned we will do things like designing the antenna and the chips that can be used with very low cost receiver design. But in the end, we landed up doing a receiver design aspect that we worked on. It was a nice experience to interact with ISRO, and I found it very good. Subsequent to my BTech, I did my MTech in my PhD in IIT Kharagpur, and with a lot of experience in robotics and automation. I then I worked primarily in that, wherein we develop systems in in robotics like industrial robots, and then we went to autonomous vehicles. In autonomous vehicles, I currently work on underwater vehicles, which are a challenging thing to be used for the Indian environment. They can be used in seas to go undetected and also detect in the resources in the sea, which are very, very useful, Earth being very much largely occupied by seas. Then we also got into micro manipulation, biomedical robotics, humanoid robotics, and all these kind of things, wherein I need a lot of manufacturing support, and I depend a lot on 3D printing and manufacturing. And that's where you see on the right my experiences with the basic manufacturing, going from a fuse deposition modeling machine, which we very long time ago we made it ourselves, but we depended on laser, more recent technologies, on laser-based technologies, which supported us to work with metals. And the first tryst with metals was in 2009, wherein we had our powder bed fusion machine from EOS, which we recently again upgraded to the most one, about which I will talk about in the talk. Other than that, we have a multi-jet curing, UV curing system, which is good for functional, not functional, but at least form-based prototyping. We also have very small micro and nanoscale manufacturing facilities, which is actually in the background, which you would have seen when I was, when my thing was live, my picture was live. There we have micro scale 3D printing, micro nanoscale 3D printing. We also have micro nanoscale 3D fabrication. I will not talk very much about it, but I will just give a brief mention of it, how we use that in variety of frontline, very, very new age technologies that are coming up in this direction. That's mostly because of my exposure in manufacturing. So while majority of my talk today will be focused on the general manufacturing from an industrial perspective, I will try to give some thoughts about how we can take it for space perspectives, space application perspectives. But then there's been a lot of trends which are driving the innovation on this. It is more like the way automation has come in. Today, if we say we are manufacturing cars or electric vehicles, I just got my hands onto one of the electric vehicles and I'm actually enjoying riding it, a green technology. And a very well-known company like Tesla has been making this. Like any other companies in India also, like Tata's and Mahindras, these are manufactured in production lines with many robots. And you can see that these robots are supporting various activities on a production line, and the car comes out of it there. If you look at the equivalent on manufacturing side, additive manufacturing today, in short, what I write here as AM, is also replacing the manufacturing shop floor. What you see on the right here is a factory with multiple manufacturing machines, each of them producing different parts, different items at different materials. They may work on different geometries. They may work on different things. And then they can do either a small volume or in a repeated manner, medium-sized volume. And very complex geometries can be fabricated and they can be put together. And they are highly reconfigurable because every time you can launch a new job through a digital process and get it printed. It is like 3D printing of a design that you are making. And I will talk about this. So that's the way future is emerging today, that manufacturing on the shop floor is being replaced by conventional machines are being replaced by these kind of machines, which will not just do things which are pretty time consuming and process intensive tasks into just simply like you make a CAD model, you share the file on the internet, and then you pass it on to the service bureau and they will print it for you. And this is a typical example of a service bureau that you see here. So it's a multi-machine systems that are coming into play. So I will today talk about generally about 3D printing, the metal 3D printing, micro 3D printing, etc. So essentially here we are talking of additive manufacturing, which is also called 3D printing. There's a minor difference between the two. Additive is more like a process wherein you add a material instead of removing material, and it actually helps a lot as compared to the traditional secondary manufacturing processes, wherein if you remove material, you incur wastage and you actually spend more energy in doing so. And that's why it is not so green in that sense. Okay. You can, on the, this is therefore, that's why called as an advanced manufacturing thing. You can also make very complex shapes, which otherwise traditional manufacturing machines, either on a lathe-like machine or a milling-like machine or any combination of these, makes it very complex to do. And on top of it, like the example I've given, if you have multiple machines, you can work with multiple materials and you can expect different properties from those parts and products made. And you can have a lot of flexibility while doing so. And accordingly, you can actually configure or plan your design to manufacture process. And this entire thing has become digital thanks to these digital innovations that are taking place these days. So that is the kind of a driving thing behind which makes it possible these days. I will not get much into this, but there are many families of additive manufacturing. In any typical course on additive manufacturing, we cover most of these. Here I will talk with respect to the one that we have on powder bed fusion, which is the where we have had recent experiences. We do also have material jetting options and UV curing that I mentioned, but the more exciting things are happening in the powder bed fusion thing. There are alternative technologies on sheet lamination, material extrusion, and also there is a direct energy deposition process about which I will talk because we are getting into it also. Then there is a 8th category, which is an hybrid category, which may be a mix of these, or they can mix with a subtractive process wherein you actually traditionally remove materials. And that is also gaining a lot of it, which is getting a lot of attention because you have benefits of both additive as well as traditional technologies, and you get a lot of new things that are happening. And I will touch upon it briefly today. In general, the transitions are happening like this, that you typically talk of digital transformation, wherein you take a CAD model. It would have traditionally gone through a rapid manufacturing process, either on a lathe or a milling-like machine, and then you take through heat treatment process and put it on maybe a non-traditional manufacturing process and get things like die inserts made. There are multiple stages you have to take through. But if you do this in a 3D printing approach, what you do is you start with a CAD model, and the CAD model on the left here is an example of a CAD model like we work on, like a impeller which is used for a heart pump, a ventricle assisted device, and you make a CAD model of it, and then you launch it into one of the types of printing process. Here I talk of DMLS as one. It may be one of these, either FDM machine or a powder bed fusion machine or even a micro printing process, and make the parts. Like here I show some parts which are robotic parts, like robotic hands, legs, joints, or these automotive parts, like these are things I will talk about later, or even micro scale printing jobs, which can be used in different applications. And interestingly, all of these go with various scales, whether be it micro or meso or even macro scale. And they are driven either by an electron, a laser beam, or an electron beam, or even ion beam driven processes which control the accuracy and resolution of what we want to work with, as well as the materials that we want to work with. So the digital era with 3D printing has actually a very wide spectrum of things. We at IIT Kharagpur have many machines of this kind. This is the initial machine which we called as M270. Then we had laser processing processes, material processing processes in our laser lab. Then we have a robotics lab, and then this is the micro 3D printing facility that we have. We have some more, but I'm skipping some of these. I also am in charge of the direct digital manufacturing lab, which was set up in 2009. We installed the first metal 3D printing that time when people were hesitant to set it up at an academic institute. And more recently, 2016, we had the microsystems lab also. Again, we had this. And only this recently, this one in 2009 has been upgraded to a more advanced system these days. We had already make parts for automotive applications, like our students developed these for Formula cars. Like this is the intake manifold of it, made out of aluminum. And the chassis, this is for a Formula car wherein this has to be custom designed, and it was fabricated in our lab and made out of aluminum. Its sump was made out of steel. This was also done in the lab. These are impellers or propellers for underwater applications. These are robotic joints that I mentioned here, which I routinely use for my robots. Like these are the legs of a humanoid robot, almost adult size humanoid robot. The gears and everything inside are made by these machines themselves. You can also do on biomedical applications like hip stem implants, which are there. These are finger implants. We got some requests from various organizations and we made them. This is what I talked about, the ventricular assist device for heart pump, etc. And this is made in titanium so that it can be made for biocompatible applications. So all of these follow what we call as a powder bed fusion process. And the powder bed fusion process is, since I'm focusing mostly on metals, this metals is something which can be used in real applications directly in a final product. So there are different ways of doing it. One is the liquid phase sintering and another is the full melting process. And the other processes are not really as effective, like you may have a solid state sintering or chemically induced binding. These are typically used in ceramics. And those ceramics, it's upcoming technology, but they don't deliver the strength as we look at. But looking at the most viable and commercially grown systems, they could be either a liquid phase sintering or a full melting thing scenario. We work mostly on full melting based systems. We use a technology called direct metal laser sintering. It's called DMLS in short. Basically, we do layer by layer addition, wherein you have at the one end, you have powder, which is passed on to a build chamber through a recoater. The recoater puts the powder on a bed, and there's a laser beam, which is typically very small dia of about 80 to 100 micron dia, and it may have a power ranging from 200 to 400 or even 1000 watt lasers are there. When you apply it on a very small area, the energy density is so high that it actually melts the powder, and then when you switch it off, it very rapidly cools and it binds to the substrate and it makes a solid part on the previous layer. And then you do this layer by layer, and you can create a geometry by lowering the middle process and let new powder be stored on top of it. So this is how it goes. We typically start with a CAD model, then you have powder, and the CAD model can be very complex. It does not matter the complexity. And then you bring it to the build chamber. In the build chamber, the laser, the powder is first coated by a recoater on a thin layer of few microns. and then use a laser beam to melt and solidify only that portion of the CAD model which is relevant. The rest all is left untouched. And then when the material solidifies, melts and solidifies, then you go back and you put another layer on top of it, and you continue this process several layers, layer by layer, and as you keep on adding, you will complete the part like this. So this is a well-known process which has been described by many, and you can see some videos here. I hope they will run. This is a typical thing that is going on about a material that we use for in a typical layer. A laser beam is applied on the this one. I think I'll mute the video. Somehow this video from YouTube is not coming. You can see here a medical implant. Multiple of these are working together. The laser beam is melting a part on a powder bed, and the recoater goes back, puts back a new layer, and then again the laser beam only melts and solidifies the material at those regions as dictated by the CAD model. Here it builds a support, what you see there, and then it builds the material also. This is how it goes on repeatedly. This is what we call additive manufacturing, which is a kind of a very state-of-the-art manufacturing. It is also earlier called rapid prototyping. It was earlier done for making parts with very complex geometry. It may have inside structures which have been, which may be of a different, like there may be paths or cavities or even channels which may be used for cooling and other things. And you can make them into this process very easily. Conventionally, it is very difficult to make dies and inserts for achieving this. In an additive process, it's much more easier to do that. What I've shown here was for metals. You could work on materials like stainless steel or reactive materials like titanium or even aluminum, or high strength materials like cobalt chrome or H13 steels, etc. There are people who have worked with precious materials like gold, etc. There is also equivalent work going on polymers, which I will not touch upon. I think there is a separate talk on that. A typical flow would be take a CAD model from a software, then the software creates the CAD model. Then from the CAD model, we create an STL file, which is a set of triangles which represent the outer surface. From that, you actually can create it's a boundary representation module. And from there, you actually slice this into a format wherein you do it layer by layer. Because the 3D model can be in any form, any shape, and depending on its orientation, you may get slicing differently. So you need a process to slice it and bring it into this form. So STL is converted to a slice format, and from the slice format, you take it to a build process, and the machine takes over from there. So the first part of it is done in software. The later part of it is done on machine with some integrated hardware software control. So our machine being from EOS, these are examples I've taken from there. So you can actually mix a complex part like this, and you can see how it is being built here. So in the interest of time, I will skip through some of these rather fast. So this is where you start with the materials, powders, and go to the part. This is also called selective laser sintering. Some people call it, some call it as direct metal laser sintering, and so on. So this is another example where the whole process is shown. The whole process generally contains these steps. We normally do the first 3 in software, 4th one is on machine, and 5th one is a post-processing activity. Just to give you an idea about what happens in the software stages, you might pick up the model sometimes from very complex shapes. Like a CT scan can actually create a data of a, let's say, a human implant or a skull data or things like that, human orthopedic implant, which can be very complex in shape. You may not have a geometry to well-known geometry to define it beforehand. So CT scan actually extracts that, and then you can recreate the geometry in 3D and bring it into a CAD software by re-engineering or redesign, and then you can optimize and create a shape. Now, in the process of optimizing, you can do a lot of wonderful things. This is again an innovation which is there. Like if I have a shape like this, a traditional manufacturing says a shape which has bolted points or mount points like this, there may be a lot of material out here. But if I optimize it, you may require many places there is no material to be required. So I can kind of optimize it and make a much more simpler shape, which would have been traditionally difficult to manufacture, but in a 3D printing, it becomes easy to happen. So here is an example of hip implant. I will skip through this, how it was done in our lab. This is the hip implant, which is done, hip implant with reduction, support reduction. Yeah, here is the example which talks about how the a design is made wherein you can have a material optimized by shape optimization, or sometimes we call it topology optimization also, wherein you can create honeycomb-like structures, which was mentioned sometime, and they make the material, the system very light, and also giving the right kind of strength, the same kind of strength that we want. Such a thing traditionally would have been more challenging to do, but it is quite easy to do in this kind of thing. Here is another example wherein if you take a bracket like this, you want to optimize it, you can bring it into various shapes like this. This is an example of a porous structure wherein you can create pores inside a material. You can control the shape of the pores by bringing in CAD model. This is called hybrid modeling. And you can bring in, let's say, this is a thing like a bifurcating arteries kind of thing brought into it, embed that into a design, and you can create a porous structure very easily and then just pass it on to manufacturing. These are very useful when you're working with biomedical systems, wherein the shapes and structures are very odd, and sometimes you need the porosity because bone structures or tissue structures grow into them and make this structure more stable for long life applications. Here is an example which is from a Renishaw, where they made a very lightweight cranking wheel of a bicycle. They could actually put it for a bicycle chain drive, which made it much lighter compared to the steel structure that we traditionally see. Then there is a bike cylinder also, which has, here is an example which has been made to actually optimize. You can see this, the porous structure or the cavity structure inside, which would have been very difficult to manufacture otherwise, or it involves many stages. Today, if you do it by additive manufacturing, it is much easier. These are innovative structures people make for different, sometimes artistic applications, but you can see how a spider-like web is useful for capturing something, etc. So they actually do additively. That's a very good example of how additive structures are made for real-life usage. This is what has led to what is called as topology optimization. Topology optimization allows us to keep that minimal material and give the adequate strength that we are looking for. Here is an example of a frame which is typically used for aerospace structures, because they want to reduce the dead weight that you carry in the aircraft due to various structures that are there. And you can always optimize that by these methods. And you can, usually we do by FEM method. And then when you land up with a shape which is very complex, that is wherein there is no stress, no material is not contributing to the load, you can remove it and get a shape. And then you can save a lot on material in this process. This is a bicycle frame made by Renishaw for their bicycle, a titanium bicycle frame. And you can see this on videos that are there. Okay, they made it a very simple, very lightweight one. And I have seen this bicycle, you can literally lift it up with 2 fingers with your hand. It is so light. Okay, of course, it's made of a material like titanium. This is another one to generate a shape. You can see the top here. This is a solid conventionally manufactured thing, but if you topology optimize it, you can get a very complex shape, much lighter in material. Another such example, which is floated around. These are all picked up from industry examples. We haven't done these here. Here is another. Here we have done it for underwater applications, wherein we could make shells for underwater vehicles, which can withstand high pressure environment from various directions just by putting ribs inside it in such a way that they can withstand it, which otherwise would have been very difficult to manufacture in regular where you weld them, you additively manufacture here, and we were able to achieve it for creating battery storage modules in our underwater vehicles. So you can also do for supports like this and create support optimization in this process. This has led to what is known as a product cycle, which is a additive manufacturing process chain. Today, many people are involved in this and they have modeling and simulation included into some of this. I thought of bringing that in this talk, but given this time constraint, I'm going to cut short of it. But in general, if I summarize it in very short way, whatever I wanted to talk about from the geometry and other part of it, we normally consider two parts. We look at geometry at one end, and then we look at material at one end. So geometry, what you see here, contributes to the the basic design, the geometric design of it. What I talked about now. Materials comes from the type of material and properties that you bring in. Then we use computational tools and interfaces to see how well these are together. And it usually involves the entire group, like the designer, the manufacturer, and sometimes even the end customer who says like, they say that this is what they want in a particular manufacturing, this one, and then you get it made. And the manufacturing and process development therefore takes place at the machine itself. This can happen on all the scales that I mentioned, whether you talk at the largest scale of aerospace and defense, or you can do at architecture. Today you see of 3D printed houses that are coming. These are pretty large scale systems, automotive systems, like I've given some examples. Very common, you will see personal products at home, like DIY products, etc. And then the minor scale, they are also going towards micro and nano scale in this process. And I will give a couple of examples on that. I think I will overshoot time a little bit beyond 3, but then I'll try my best to cover a few of that in the interest of everyone. So what it has led to is we are going back to traditionally to what is called as craft manufacturing, wherein the consumer and the artisan work together to make a product. When industrial revolution made these to go through factories and standardized products, today the direct digital manufacturing brings personalized products in a local manner, and it got facilitated because of these additive processes. So when we do this, we actually in a lab like our institute, what we do is we look at variety of things when we implement it. What we do at our institute, we look at a typical process and say what are the contributing factors in it, and each of these factors we then thoroughly experiment with to optimize the product. Like in this case, if I'm doing anything with a laser-based product, powder bed fusion, it depends on things like the laser power, the scan speed, the hashing distance, and scan strategy. And they influence the process time, the surface roughness, the mechanical strength, dimensional accuracy, and other kind of aspects of the product. And then if you interplay between these, we know which is the right combination of these parameters, which will give you the best quality output. So we create models of this by laser material interactions, and these allow us to actually get into deep of what will be the final property that you will achieve. So there's a lot of optimization involved in it. Sometimes you increase the power, sometimes you increase the deposition rate, sometimes you increase the feature quality, and there's an interplay between this, and you have to choose that sweet spot which brings up what we call as a process map, and that process map becomes relevant for us to implement as a recipe which goes to the industry, and we are involved in doing that. So to do that in our lab, we have used these machines and we have rigged them up with all kind of monitoring processes, which allows us to say what happens inside the process when the part is being produced. So towards that, we have these laser-based machining process that you see. There are snapshots that we take through a thermal camera, and we can detect from that like what is happening on the process. Sometimes it does not go well as planned, and it may introduce defects. So we look at defects by looking at the intensity of the laser energy, which is varying with the various process parameters that we change, or the spatter, which shows how that plume is of what height, and it is ejecting too many particles, or it's likely to create more errors in the job. Like there may be pores, or there may be lack of fusion faults that may happen. So we need to capture them early. So this was what we did earlier, and we got some interesting results out of it. Later on, what we did was we actually went into upgrading the machine so that we can actually capture these more systematically in a very professional manner. So the upgraded machine has a camera which captures this at one end, and it has a set of laser diodes that we see here, which monitors the back radiation, and they give an impression of what is the temperature that is on the build screen. And then you can reconstruct and see how the melt pool is forming, and that melt pool forming and cooling rate will tell us what will be the property that you are going to achieve in the process. So we monitor them through devices like this, which are allowing us to capture all this. So here is that we call this in situ monitoring. Like you see a typical thing here, I'm doing here a job of a BHEL turbine, which is a closed impeller. And while it is being manufactured, we collect data of it through a camera, as well as the CMOS camera, which gives us a picture of the bed, as well as a scanner, which tells us what is the temperature. And then we reconstruct that on the right-hand side here as a video. This is playing a video, I think. I don't know why it's not coming here immediately. Okay, so we can reconstruct that at this side. Here is the video, yeah. So we actually capture here the various backscatter images, the radiation on here on this screen, and here is the thing. This is constructed from whatever is happening on the job, and you can do it layer by layer. And once you reconstruct that, you can when you capture this live, we can then use it for reconstructing the job and look at if there's a possible defects. So this is how we started with. We started with a CAD model of an impeller here. It had internal support structures, and these support structures here they are needed because the manufacturing system will fail otherwise. But when you make them, you don't like to keep those structures. You have to mill them out or remove them. They create a problem. So we actually collect all this data, analyze, and see where they are possible hotspots or things which may cause problems, because these impellers by BHEL will be used in plants, and they are supposed to have a long life of 15, 20, maybe even 40 years in gas turbines, and you cannot afford them to fail. So you need to have a very perfect part being made here. So what we do is we do what is known as IR tomography. We construct the body. Let's say this is a coupon that we made, and we know what happens at the base as it builds. So this is a reconstructed image. And in the reconstructed image, we know at the interface between the support and the body, there is a lot of high energy temperature developed there, and it is prone to failure at that point. So we are devising ways of minimizing this kind of thing, so that a body, when it is put to use, we will have that. So we reconstructed for the same job that we see. We could, since we did this we could actually build this up. This is not in the same scale as what you saw there, but I can see here the supports as well as the internal ones, and I can examine this at any cross section and then come up with alternative recipes to achieve this. This is an example which shows that where is the likely hotspots and chances of having defects inside the part. As I said, if I put this for use in in real life applications, you don't want this part to fail. It has to withstand a long life of maybe 40, 50 years in turbines, and the failure expectations are very less there. So it's pretty challenging to do it by this method. We depend a lot on international technology, but hoping that by doing this, we will be actually coming up with our own technologies to help this out. While this is a technology, what I call as the laser powder bed fusion, there's an alternative technology that we are exploring, and I mentioned there is what is called as direct energy deposition. Direct energy deposition here allows us to also deposit the metals along with the material from a nozzle, as well as from a laser going along with it. This is not a powder bed system, and it is something which can create odd shapes. This machine we are just getting, it somehow could not be installed due to certain problems that we had in our delivery. On the right side, there is also something which is a similar kind from the same company, which makes printed electronics. We don't have this at our institute, but I will talk about something related to it in a few minutes. So this is typically you fabricate here with the machine that we have. It uses something called lens technology, that is laser energy based near net shaping. They trademark that like DMLS, and then that can make parts on complex geometries like this. This is a fabrication application. You could also use it for repair. If something is damaged, you can only fill up that part which is damaged and repair it. You could do a hybrid process wherein you can make and machine it also. And that's what we have actually procured in our lab. It unfortunately could not be installed because something happened during shipment, and that is going on right now. This is the repair process, how it is being done. Okay. And this is a hybrid process wherein you actually manufacture and also machine after that. Once this is completed, machining, this is a deposition process. After this, I think you will see a machining process also taking over on this. You can create a complex shape, and then you will see here a machining also done to remove all the excess material, and you'll get a good surface finish also here. So it is generally done in controlled and inert atmospheres. This is what we have at our lab. We got it in our advanced manufacturing center. Yeah, it's not yet installed for functional, but we are already practicing with its software and working with it with several scholars working on it. They have a lot of capability of bringing in different kind of materials. Generally, we use powders of different kinds. Here, the powder sizes are a little big, and build rates are also very fast as a consequence. So you can actually work with, again, same materials like stainless steel, nickel, copper, carbides, and titanium and other materials also, which is now happening. Here are a few examples of these. People have used it for satellite housings. I heard ISRO is having some of these done here. Then not in our center, but elsewhere. Then repair and replacement, it is possible. And you can have metal matrix components of also doing. You can mix materials and create in this also. That is another advantage of this, this process. It allows us to make many parts of extreme complexity. Conventionally, it is otherwise not easy to make here. So here again, similarly, housing, turbine blades, industrial components. These are generally you'll get very bad surface finish here too, like in powder bed systems. But if you have a hybrid system, you can machine it and get very good things here also, like here. Few more examples of this kind. These are from the slide companies, Optomec. I thank them for providing these slides because our machine is not yet available, operational. New materials are also being developed on this. And you can have carbon reinforced nanotubes, CNTs, carbon nanotubes reinforced nickel alloys, boron reinforced titanium alloys, and all possible on these machines also. Then I talked about printed electronics. Today you can actually print something on electronic materials, on things like you can make sensors, you could do packaging, you could do antenna. We tried to do this with the FDM process, but there are a lot of things we can do internally with similar processes also. You can actually put in ink onto materials, and the inks, conductive inks, or they could be also materials of different kind, which can mix with the different matrix, and you can have electronics also happening in this process. So these are called electronic ink, which are actually small droplets which are aerodynamically focused, and aerosol jets are deposited, and you can create these also. This is another innovation that has taken place. It is coming from this company called Optomec. What we do at IIT is we do at micro and nano scale. Maybe I'll just take another 3-4 minutes and wrap up this. We can print things using femtosecond lasers and make parts at extreme small scales. I call that micro and nano scale printing. We can use it for various materials, not necessarily metallic ones like I mentioned. They can be electronics, they could be on MEMS, they could be optical, and even bio nanomaterials. This is a setup which we have got from Nanoscribe, a German company, wherein you can actually achieve feature sizes of the order of 1 micron size, and the resolution is down to 200 nanometer, which is the feature, this one of that laser that is used here. So here are scaffolds made at this 3D scaffold at nanoscales. Their applications tend to be like scaffolds for cells, which may be used for capturing bioorganisms like they do in COVID or other things, and then they do tests to characterize what it is. It could be used for micro-optics, it could be used for microfluidics, MEMS applications, massless photolithography, or most popular, this one happens to be in 3D photonics and wire bonding in optical integration. So it uses a technology called direct laser lighting, wherein you focus a small beam of light and you modulate its intensity and amplitude by a process called 2-photon polymerization process. It's a near infrared laser having a wavelength of about 380 nanometer. 760 nanometer, 780 nanometer, which at half its length you can get its resolution. You can work with photolasers like positive, negative, and you can write on top or use a dip-in laser process. The voxel size is 200 by 200, 300 nanometer, and you can directly build parts in 3D. There are people who worked on this and made micro robots, like this is Athiya Zurich has made micro robots which can be swimming in body, and they can deliver drugs at remote places for cancer-like treatment, etc. These are magnetically guided robots. We are trying to build some such things. And whenever we make such, you make a large number of them in the same build, and they can be done very easily on this. These are called magnetic helical micro machines. They can be fabricated, and we have been making some of these in our lab. Here is how this thing works. This one I picked it up from internet. Here is an example of how this works on. Cut down the sound. 3D printed.
The miniaturization of optical and mechanical components, as well as fully integrated devices, can bring great benefits. Today, additive manufacturing.
So you can actually print on chips, on top of a chip also, a structure. And you can actually create optocouplers on the chip and achieve this on it. Okay, I think the internet is slow or something is there. It actually makes some of these videos a little slow. You can check videos on this on the internet. There is another example of how this has been made to build a small castle-like thing on.
The following video shows 3D printing of a castle via multiphoton polymerization technique,
This was done from TU Wine at
also short
Austria.
called laser-based 3D printing.
So it can build a
The
castle.
laser scans through the volume of photosensitive material. Locally induced photopolymerization solidifies material in accordance with the 3D model. Once a layer is finished, the laser focal plane moves to the next layer. The true 3D capability of the method eliminates the need to deposit material layer by layer. Due to non-linear absorption, spatial resolution in the submicron range can be achieved. Scanning electron microscope image of a castle printed onto the tip of a pencil.
So this is to give you an idea like how they make at that small scales. Okay. And the lack of time, I'm trying to skip some of these. So what we do with such kind of machines is we are making micro nano robotic systems, tips of AFM manipulators. Okay, we want to use this with micro platforms. This is because of my robotics background. This is a part of a swimmer that we are making here in this. Then we are also trying to make micro tweezers, a heat engine, scaffolds, tents that could be done by direct or indirect 3D printing processes, and create micro machines, which are the things of the future that are happening with these kind of, you can actually build the machines in 3D. Other group members, this is the group, Professor Bhakta from physics department, he works on micropillar cavities with this, and they make very fine cavities for resonators, optical resonators that are useful in different applications. So this is the kind of stuff that people work with this, and this is to give you an idea like what we have done. As an example, I did it a long time ago. We have our main building here, which is the Institute's tower, which is about 10-story tall. We made a 3D model, printed model, 3D model of it, and this 3D model of it was 3D printed and made and seen in a scanning electron microscope. You can see here the scale is 20 micrometer, and all features inside this are of the order of few hundred microns, a few hundred nanometers, and these are useful for making sensors that can be used in MEMS devices. This is another that resonator microcavity pillar made in 3D. Okay, this uses the other technology in the same lab in which I have. Yeah, I think this went out of order. So this comes to my last, this one in summary, 3D printing and additive manufacturing, it is triggering all kind of new innovations. It is slowly maturing, wherein a lot of digital connect is taking place from the design to manufacture, much more than what we have seen before. A lot of types of new materials and processes are involved. A lot of new exciting technologies are coming in the workflow. And when you add modeling and simulation with geometry, materials, and properties, its adoption for this one and its confidence in use has increased a lot today. In conclusion, I would say it is revolutionized the way product manufacturing and process innovation has taken place. New and complex geometries, processes, and macro to meso and micro scale is becoming feasible today. So with this, I will end my talk. I am very thankful to many of my collaborators who have added to this. if you have any queries, I'm reachable on these contacts. So this is my last talk. I'd taken another 20 minutes more than the time. My apologies for that. Okay. Please.
Thank you so much, sir, for such a wonderful talk. And you have really taken us from a macro level 3D printing to an nano 3D printing. So the session is now open for question and answer. So if there are any questions, participants can ask questions. Are there any questions on YouTube, Hari?
No direct question. I will ask one thing with Professor Kumar. Nowadays, we are making a lot of these mobile telephones, and I think there's a plan to make chips in the country, microchips. So,
Yes.
as you said, no, you did some work for the Navik also from SAC ISRO. So, what is the status as on today? Can we make this mobile telephone chips in the country? This technology is available, and how much role is there for the mechanical people in that?
Thank you for the nice question. I will take this in two parts. Part one is the chip making itself. The chip making process is a process wherein you typically work with building the electronic circuits inside by typically done on silicon wafers, and you make the devices on it using conventional manufacturing, which is a mix of etching and lithography and other processes to create the devices inside. That is very much a high-tech area of electronics manufacturing. On that, my lab, or as a mechanical engineer, we have very little inputs that we can do. Though there are some new developments taking place on it, but they can't be applied on the mass scale like the way those chip manufacturers make for millions of chips in one go at, let's say today, 5 nanometer or even 2 nanometer technology people are saying from electronic perspective. However, the second part of it, if you are saying from the mechanical engineering point, and particularly when I got excited with the NAVIC technology, is suppose you want to build a structure on top of the chip, and that was a video I tried to play. If you want to build a structure on top of it, maybe let's say an antenna, or you want to build a structure which is used for a MEMS sensor which senses vibrations in 2D or 3D, or it is picking up some signals in other directions, then that structure will be a 3D structure. And ideally, if that structure is built on top of an existing chip, then you minimize a lot on top of doing the connection between the device and the chip. You save a lot on power, you save a lot on the packaging. So you can think of an on-chip antenna. You could think of a antenna which, like they do for these cell phones, you have antennas are embedded inside the cover of this. That's why we can't open this. They don't advise us to open this cell phone out, because if you open it, you probably are going to break up those antennas. They are kind of deeply integrated. So the same can be done at that level, and that's the level wherein 3D printing comes into play. The next level of 3D layered chips are also coming in, and again mechanical engineering will come into play, because the conventional chip making is a 2D process, and if you make it 3D, there are issues with heat dissipation and the challenges of dissipating as you make smaller and smaller, very high currents flowing through that small areas will create small currents in small areas, but they create high energy flux and they get heated up. You need to cool them off. So creating 3D heat sinks for that, which can dissipate this very fast, is also a new concept which is coming by 3D printing. So there's a lot of domain here for mechanical engineers. And though the basic fabrication of a chip, we don't get involved, but soon I think mechanical engineers and the basic thermodynamic engineering is going to drive moving that also. In about 20-30 years, I would see 3D chips coming out, and that's when we will again get attention to.
Okay. One more thing, it is not a question, rather I will ask your advice. A lot of young engineers, diploma and degree holders, they are attending this particular talk, and they will have to make their careers. So can they select the subject of micro and nano machining in the field you are working, like additive manufacturing, as a career? Or they can start doing some sort of business to fulfill the need of the country?
Yeah, that's
What is your advice?
That's a very nice question. The need of the country is, yes, we should be doing that. In fact, all the major countries which took a big step on this a long time ago have become world leaders, like Israel, like Taiwan, and Korea. They have these facilities wherein they actually do these chip making companies and do 3D and micro nano machining and manufacturing processes there. Others who have been late into this have lost out a lot on it. In fact, some are there even in, let's say, Switzerland and other places also it's happening. They are small scale economies. India has a potential of getting into it. Unfortunately, due to past situations wherein we could not have a good fab processes, it could not take off. Like, we are not known to be good in manufacturing as such. But by venturing into it, when the demand is high, one has a potential of becoming a leader in it. Today, there are startups which are doing this, and there are not many. Those who are bold to get into this can get in. It's a little bit of cost intensive, but with a supportive government, whenever they are open to such kind of things, I don't think we should have the difficulty in getting into it. I would encourage students to get into it, at least as a small project like way to begin with and get their hands dirtied out, and later on see how they can venture into this. That would be my advice, because these are capital intensive, costly setups, which if you get an exposure here and there, like we do in our lab, the lab behind me is a very small scale lab. It's not a big fab lab, like very expensive to run like in ISC Bangalore, but we can do a lot of things inside that within this itself. So one can think big, but do with small setups and achieve something. It's possible. And young people can take that those bold steps if they get the confidence on it.
Thank you, sir.
Sir, I have one question, like one or two questions. Sir, when you spoke about the laser-based 3D printing, and you spoke about two-photon polymerization, because that depends upon the nonlinear optical properties of the material. So if material is not having a good nonlinear optical response, and then we plan, suppose somebody plans to make a material which doesn't have a good nonlinear optical response while making a 3D printed object. So in that case, how to go about it, or whether there are any limitations in that case?
Yeah, interestingly, currently the materials that have been created on these machines, for these machines, they are a bit proprietary, but they happen to be also compatible with the materials that are used for chip fabrication. Okay. These are called photoresists, and they can be engineered as well, so that they develop response to that nonlinear response to those laser energy that is pumped in at a very short microfemtosecond bursts that we give in there. Now, such materials can be engineered. They have to be kept in a particular manner and stored and used, like, and then you do achieve that. Otherwise, you have to optimize. Like we do in others, we have to create recipes Optimization means you create recipes for those materials. It is no doubt a science in itself and people are working on it, but it is no longer that complex a science that you can't do it. People are attempting to do it, and it is possible. Like today, materials are even going into biomaterials, biocompatible materials, nanomaterials. We could actually use some can be synthesized, some can be materials which you can get from the natural materials itself, biofabricated materials. Like we try to use 3D gels. We get gels from which you try to do 3D printing, nano gels. And there are a lot of interesting things which is happening from a material science perspective also.
Okay. Thank you. Thank you, sir. Hari, are there any questions on YouTube?
Ask Amritanshu whether he's watching YouTube. Can
Okay, sir. There is one question from YouTube. A student wants to ask what kind of designing softwares are used for additive manufacturing?
Today, practically all kind of CAD softwares that are available can be used to do additive manufacturing. Some of these are commercial. Most of these are commercial, like you start with SolidWorks or AutoCAD, or AutoCAD is called now Fusion 360. Then you have CATIA. Siemens has got NX CAD, and they all go all the way up to manufacturing also. Today it is happening a lot. You have open source software also free to use, like CAD softwares which can be doing this, and you can do 3D printing at home. So I'm forgetting that Cura is the printing software, and the CAD software is FreeCAD. So you can, there are many of these which are available these days, and we use it in our labs a lot. I mean, for first year students, etc. You can do it at home. You can learn a lot in this process.
I think basically we need any CAD software which can convert the file into STL format.
That's right.
That is what 3D printing accepts, STL file.
Yeah, but there are many softwares today, they can do it automatically. So CAD is the first stage. So CAD softwares will do that for you. So my last slide was about the Advanced Manufacturing Center. I forgot to talk about it, but the Advanced Manufacturing Center here has all these facilities and many more. You can look at this site and update yourself and what more you can do here. It's a government supported center for excellence on manufacturing for heavy industries.
Are you doing any work for the like our launch pads, which we have actually Hurikota? Whether any time ISRO has contacted you for make?
I don't think anybody contacted us.
Anybody contacted?
We put one proposal for making those storage, what you call as hydrants.
Okay.
Those 3D print along with that under some scheme of Indo-German collaboration for new material. We are waiting for outcome on that. It's not with ISRO, but it is with the DST.
Chintamani, what happened?
Yes, sir, I'm here.
I think there is no question. We can stop it.
Yes, sir. So thank you once again, sir, for giving such a beautiful talk, giving us insight from the macro till nano 3D printing aspects. And I'm sure all the participants must have enjoyed listening to you.
Thank you very much, sir, for accepting our offer and delivering a nice talk.
Thank you. It was a
Yeah.
pleasure talking to you all, and I hope I was able to satisfy some of the requirements of the day. Okay.
Thank you, sir. We will be in touch.
Thank you. Wish you all a safe time in this difficult times, and stay safe. Yeah.
Thank you, sir.
Thank you, sir.
Thank you.
I think Dr. R.M. Vijikar Rao and Professor Shukla both have joined. Yeah. Sir, your mic.
Yeah. Unmuted, sir. Thank you.
Okay, very
Good
good.
afternoon to
Good
everyone
afternoon.
and to yourself, sir.
Thank you, sir. Thank
And
you.
eagerly waiting for Dr. Rao's talk.
Yeah. Yeah, Rao sir, are you there? You have to unmute your mic. That red color button you have to press.
Can you hear me?
Yes, yes,
Yes,
yes.
sir. You are
Very good, sir.
very much audible.
Yes, but am I visible? That's next question.
Yeah, you can see that other button also where you have got a video camera. That also you have to click. Then your photo will come.
Video camera, where is it?
Near that only where you had the last button at the bottom side.
Sir, it is next to the mic button.
No, he is operating from the mobile.
Okay.
So from the mobile at the bottom, sir, you shall find after the mute, the second button from the left, start video.
Rao, sir, you have to unmute. You have to press on that mic button.
You have wrongly pressed
Yeah.
that
Otherwise, we
button.
can't hear you.
Yes, now you can speak, we can listen to you, but your video is still not coming.
Yeah, that video, where is that button? I'm not sure.
There is a button next to this, which you
The video
pressed just
mark,
now.
video icon, that video camera icon is there. Just click
No,
on that.
I don't have it on my mobile monitor. That's the problem.
There should be 2 or 3 things should be coming near this.
So excuse
So
me,
you will
sir.
find, sir.
Yeah.
Hello, excuse me, sir. This is Amritanshu. Sir, Rao, sir. If you can just look at the bottommost part of your mobile, then
Yeah.
from the left you see the icons are there. The first one is the mute, followed by the second icon which says start video. So if you tap over it, your video shall come.
Wait a minute.
Not this one. Again, you pressed wrong button.
I think you can hear me now.
Yeah, we can
Yeah,
hear
we
you,
are-
but
yes,
not
sir.
able to see you.
Video is not running.
The video is the problem. I don't know where that video
Okay.
button is. It's
Okay.
not-
Anyway, sir, we will manage with this. At least if your audio comes, we can manage.
Yeah.
Yeah, Chintamani, briefly you say, then I will introduce Rao sir, whatever I do.
Please.
So now we proceed with session 2, and session 2 is going to be on the polymer composites, and it is going to be an understanding for high-end applications. It will be given by Dr. R.M. Vijikar Rao, ex-head FRPD, National Aerospace Laboratories, Bangalore. Sir, we are very much fortunate to have you for this session, and I welcome you all on behalf of all the organizers of this event.
Okay,
Thank
thank
you.
you, Rao sahab, for joining us. Just for the
Yeah.
audience, I'd like to say a few lines about Rao sahab. He is a very senior and experienced scientist from National Aerospace Lab, CSIR, Bangalore. And he's around 75 years now, very senior person. And after retirement also, He is very active on WhatsApp and sends a lot of good technical details after reading all the newspapers, etc. He is an expert in
Hello.
No, I think there is some network issue from Mathur's side. Just wait for a few moments.
Yes. Am I audible?
You're audible, sir.
Okay, fine. But the video, I don't know. Sorry. Nowhere I could see a button. Stop. Hello. Any problem?
Hello. Rao sir, you
Yes.
need not worry. You are connected and there is no problem. Actually, we have lost Mathur sir owing to connectivity issues. So we are just waiting
Okay.
for Anil sir to join so that we can formally
problem, I will
begin
do.
the session.
Yeah. Because I'm a bit new to this technology. So I'm wondering if there is a problem from my side.
No,
Okay.
you need not worry. So you are very well connected and we can hear you perfectly well.
No, I just now.
Unfortunately, I'm not seeing any video button here. I don't know how to show my face. That's the problem.
Actually, there was some power failure at Mathur sir's home, so he's just rejoining in 2-3 minutes.
Okay. In the morning, we had a dry run. Actually, we were able to see one another. There's no problem. And speak also.
Because I believe, sir, your presentation is with Mathur sir. So
yeah, he will run the slides. I will do my explanation slide.
So he had just requested that he'll be joining in 1 or 2 minutes.
No problem. I will be very much here.
Chintamani sir, in the meantime, when Mathur sir joins, that is, you can, that is, I suppose there is an option from the part of host also. That is, you can prompt Rao sir to switch his video camera on. If that is possible, then he may find it.
Let me try that.
See, there are 5 buttons here, the bottom of
Yes,
my
sir.
mobile.
Yes, sir. Yes, sir. Yes, sir.
Hari, are you there? Can you try?
Wait a minute. Start my video now. The host
Yes,
has
yes,
asked.
yes, sir. Yes, sir. Now we can see you. Now we can see you. Welcome, sir.
You can see me.
Yes, sir. Perfectly.
You can hear me too.
Yes, sir. Yes, sir. Welcome, sir. Welcome.
Oh, wonderful. Then I have to see the slides. Dr. Madhurji will project one by one.
Yes, sir.
That's the next step. Great.
As we can see, our guest, our main organizer, AC Mathur sir, has rejoined owing to a little bit of power cut from his end. So we are really sorry for the small inconvenience that had happened both to the honorable speaker and as well as to the participants. So we shall be resuming the live session of the honorable second speaker of the day in a few moments. So right now we are going for the technical setup and all those things. So dear audience, honorable speaker sir, and the participant students, we are just beginning within a couple of minutes of time. Thank you.
Thank you, sir.
Hello.
Hello.
Oh, yes, sir, I am back. So there was a power failure here, so my internet was also down.
Anyway, all kinds of challenges.
Yeah, so now we can see Rao Sahab also. Your photo is coming, it is good.
Very kind of you.
Yeah. So, in fact, Rao Sahab was trying, never gave an online lecture. He was trying since long.
Yes, yes.
And a lot of pains he has taken to deliver his talk. And today around 12 o'clock, he got success in downloading the software on his mobile Zoom and send me his presentation. So I'll make a presentation from here. Request all the young boys, those who are attending his talk, so that Rao Sahab has agreed for delivering a talk and sharing his experiences with all the young people. So thank you very much, Rao Sahab. And he was the person who started the FRP division at NAL, and that division has grown and did a lot of activities in glass fiber and carbon fiber, and did a lot of work for ISRO as well as for other industries, made a lot of wind mill blades. Then he has made some glass fiber radomes also for Bharat Electronics Limited and so on. The list is very big. And Rao Sahab is a member of many journals committee. He is editor of many journals, paper reviewers. He did his PhD from Indian Institute of Science, and the PhD also, the topic was very interesting. I think he will tell that also in his talk. The topic which he selected for his PhD was all related with the space shuttle disaster. So like that, so without taking much time, I will share his presentation so that he can start his talk.
Thank you, Madhurji.
Thank you. So, sir, I am sharing the presentation.
Yes, please. I'm ready with my desktop with the slides.
Yeah.
And as you say, next slide, I will speak about it.
Okay.
Yeah. So I'm waiting for your slides on my mobile screen.
Sir, minimize that window, sir.
Yeah, can you see the screen?
Not yet. I'm getting that.
Okay, still not shared.
They have to say something, do something here at the bottom. No.
Okay, yeah, it is there. Wait, it should come. I will stop share and then again share it.
Yeah.
Share the screen. Is it coming now?
No, not yet.
At our end, sir, we can see.
You can see it, Chittamani?
Yes, yes, sir.
Yes, sir,
Okay.
it's visible. Rao sir, I just would suggest you that what you can do is try to swipe left the screen.
No.
Swipe left.
No. Actually, Rao Sahab is having his laptop. This presentation is there on his laptop. So he will start from there and speak from the mobile. So Rao Sahab, your first slide is there. You can start.
Oh, it is there now. I can't see the slide, but I can explain it.
You can see on your laptop.
Yeah,
first
laptop,
slide.
no, desktop, I can see it now.
Okay, desktop. Desktop you can see and then explain. This is the first slide I have opened.
You please do one thing. You say next slide, then I'll go to the next slide. Slide number 2, 3, I see challenge, right?
Should I go to slide number 2 now?
Number one is already over now. First, I'll thank all of you for this wonderful opportunity you have given me. Without
Okay.
taking much time, we'll go to the slide number 2, right?
Okay.
So in the slide number 2, which is a
wait.
brief outline of my presentation. Can you hear me?
Yes, sir.
Okay,
Yeah.
so I'm going to talk very important things in this presentation. One is the saying that composite concept is nothing new. It is age old. The human bone is a composite. Human hair is a composite. And even fibers are composite. So I won't go into details. Everybody knows about it. The concept of composite is that every material in nature, right from the primitive age to today, has a strengthening phase, a fibrous phase, and a what you call bonding phase, that is a matrix. So if you take the human bone or the animal bone, it has a collagen fibers and a hydroxyapatite matrix. Or if you take the plant fibers, they will have cellulose fibers and lignin matrix. So we are inspired by the nature, and so therefore the concept of composites nothing new. We are only copying the nature. So I'm going to talk to you about the fiber reinforced polymer matrix composites, a special class of polymer composites. So I'm going to discuss about it, what are the various composites and how these polymer matrix composites have been chosen as the new age material. And there are constituents in that. That is a fiber part which reinforces, and the matrix part which binds it and gives it shape. Then there is what is called, each has its own functional roles like responsibilities. And I'm going to talk quite a bit on the structure to composite property relationship because that is the central idea of my lecture. Then a few issues about the technology, about the economics of it, then applications like high volume, high end, and finally a way forward. What is there in future for these polymer composites in terms of new materials, new processes, etc. The next slide. So next slide, Madhurji.
Wait, sir, I will tell you. Yes, go ahead.
Slide number 3. I will say this is a paradigm shift in the world of material. Earlier, we used to always say that anything that is not a metal is a non-metal, like metals like iron, copper, aluminum, and their allies like the bronze, brass, and non-metals are like polymers, glasses, etc., but ceramics. But today, we are in the age of engineered materials. That is, we don't just use the material as it comes, but use the material, we make a formulation of it to suit our application. A very, on a humorous side, like a kitchen, you bring rice, you bring dal, etc. You bring all kinds of parts with that. It's a composite, something like you get some existing materials, whether man-made or from nature, and then put them together and make a recipe. There's edible. This is a structural material. So you make a composite structures of different functional uses. So in the earlier class of materials like metals, metals are mostly corrosion prone. They are very heavy because densities are high, and damage tolerance is also not so good. And they are highly not so good energy efficiency point of view because most of them, they have to be processed by high temperatures, high viscosity, etc. But to answer all these problems, in the aerospace industry, we need to have materials without that they are corrosion proof and they have high specific strength and specific modulus and damage tolerant and efficient energy-wise and eco-friendly wise. Therefore, the single answer for all this is a unique fiber reinforced polymer composite because they provide you a lot of ease for manufacturing and modularity in construction. Like we have in the kitchen today, if you order a kitchenette or you order a a wardrobe or a bed, it comes as a modular package, just goes through a narrow door into the house, then later it is dismantled and reassembled. Same way, the composite concept is that you can make it modular, a huge structure like a radome, or for example, the aircraft structures or space structures, which are very large and complex. You can make it in small pieces and then dismantle, pack, and take to the site of installation, and then again reassemble them. The radome is one of the best examples. Unfortunately, I'm not able to show you. I have got a small radome model which I have made for ISRO, Dr. Madhurji's parent organization sometime back. Anyway, all this gives you a lot of ease of transportability and on-site installation, maintenance, etc. So here we'll go on to the next slide. concept of a composite. So
Okay.
the slide number 4, right?
Yes.
So here I will call it unity in diversity. The polymer matrix composite is a very good example of unity in diversity. On the left side, you see in the picture a schematic diagram of the fibers, the hatch portion, and the matrix, a thin black line. So the fibers are separated by thin layer of matrix, and the matrix, which is a polymer, also impregnates or wets the fiber very nicely. And then you put them together and make what is called a composite of the fiber and matrix. But what is most crucial here is the interface. That means a very good bonding between the strong fiber and a bonding matrix. The interface is like in human relations also. If two people want to talk to each other, we need an interface, sometimes an interpreter. And somebody now, Dr. Madhurji and his team is actually the interface between me and the audience. We are actually a composite community now here. But why we go to the fibers? To the right side of the slide, you can see on Griffiths. He is very familiar for those who are in the material science. He has done a lot of experiments by drawing fibers out of glass. And the thinner the fiber, the stronger it is. So he has proved by this curve that materials in their finer form are stronger than when they are in the bulk form. The easiest, very ordinary example is you take a sheet of glass and drop it, it cracks and breaks. But if you take a fiber of it, it doesn't crack. So that sums up the reason why we take finer fibers to reinforce and make a very strong and stiff composite materials. Next slide is a composite superiority. See, the composite superiority we have to establish from different angles here. If you see the left side of the slide, the column diagrams, there are 5. The first one on the extreme left gives the weight advantage. The composites always give the lightest weight structures. And next column diagram is the thermal expansion. The coefficient of thermal expansion is very, very low or very zero if you go to the carbon fiber composites. But the expansion is very high in metals, especially in aluminum, more than steel, as we all know that. Therefore, if you are making very dimensionally critical structures like in aircraft and space, more so in space, they should not expand or contract under extreme conditions of weather, like temperatures, high temperature, low temperatures, cryogenic temperatures for that matter. Therefore, the composites are the best answer, polymer matrix composites, and ceramic, of course, at very high temperatures. Then you have this stiffness. Stiffness is a measure of the Young's modulus, that is the slope of the stress strain curve. So the stiffness is very important to resist the bending. And the composites again score over aluminum and steel. And next, the 4th column diagram from the left, you have the strength. Strength-wise also, composite materials are stronger than steel or aluminum. And if you divide all the strength or stiffness, the density, you get much higher specific strength, specific modulus. The meaning of it is that for a given strength or stiffness, what is the weight penalty you pay? For metals, it's very heavy. For composites, very light structures. So the last slide is fatigue. Fatigue is a cyclic loading phenomenon, which is most critical, especially in aircraft structures. So the aluminum is very prone to fatigue crack propagation. The advantage of composites is that they are fiber reinforced polymers or plastic. Therefore, the fibers act as stress crack stoppers. That means they will not allow the crack to propagate. Therefore, the fatigue life, that is, if you take the number of cycles versus the load you put it takes enormous lakhs and millions of cycles before it fails. So, but there are drawbacks. We should not say that polymer matrix composites are always good everywhere. They have the problem of delamination. That delamination, that means layer to layer bonding, if it is weak, they may delaminate, but we have to address it and take care of it. So to the right side of this slide, number 5, just the Ford Motors had done an experiment long back by replacing a steel car with the carbon fiber composite car. And they found that the steel car that traditionally, it was weighing 1,200 pounds, has come down to as low as 590 kilograms. That means more than half of it is weight reduced. That is the advantage, because carbon fibers are only 1.8 density, steel is 7.8. Steel is about 4 to 5 times heavier. But the advantage is that because it's a lightweight car, you have the advantage that the fuel consumption will be very less. And there is what is called ride comfort in automobiles. That is NVH, noise, vibration, and harshness or harness, something like that. So it will be less noisy and it will be vibration damping. So if you travel by a composite car, you will feel for it. If it's bumpy roads and very bad roads, they will not transfer that vibrations to your body. They damp it. Therefore, that is one of the advantages of vibration damping. So there are many other advantages. We can go on talking and talking, but good enough. This previous slide sums up a lot of these advantages. Now here I'm going to try to, in the slide number 6, the composites with a difference. Now, on the top, you have the polymer matrix composites, briefly PMCs, then the metal matrix composites. That means the matrix is metal, but the fiber can be anything. Ceramic matrix composites, ceramics, like alumina, etc., or silicon carbide. There are many. Then in carbon-carbon, the matrix is carbon, the fiber is carbon. In fact, the carbon-carbon composites can withstand 2,000, 3,000 degrees centigrade continuously. They are mostly used in the re-entry vehicles, the heat shields, etc., where the temperature shoot up momentarily to thousands of degrees. Only carbon-carbon composites can withstand that. And the hybrids, mixtures of all these. But what I want to here emphasize is that if you see to the right of the slide, there is a T, that is temperature. If you want to go for higher and higher temperatures for applications, you are actually going away from the polymer matrix composite. On the left side, the size, the arrow is going the other way, reverse. That means when you go to the larger and more complex structures like the aircraft, radome, and many other metal bodies, or even space structures, you go towards the polymer matrix composite. That means polymer matrix composite today score when it comes to the demand that the application need very large structures, and very large structures cannot be so easily made with ceramic or metal matrix composite. So that sums up the reason why we are today talking of the polymer matrix composites, PMCs. The next slide, slide number 7. Am I going all right, sir? Madhuri?
Yes, yes.
If you interrupt me, if there is a problem, right? So am I audible?
Yes.
Thank you. So now I'm coming to the central idea or the focus of my talk, the structure versus composite property. Now, normally we say structure property relationships. We are very familiar in case of material science or metallurgy, where metals are isotropic, homogeneous, single-phase materials. There, the structure implies the microstructure. At the microscopic level, we do it. We actually find it by the electron microscopy and more powerful microscope, and see how the atoms or the crystallized structures are all arranged and how they influence the properties of the material, the metal, for example. It's thermal, mechanical, erosion, corrosion properties are all governed by microstructure. But here, I thought, why not I use that concept? Because we are inspired also done by metallurgy, because material science connects to metallurgy. Now, material science aspects we should bring into polymer composites also. That is one of the purposes, of my studies. Now, here the structure is split into two parts. That means the composite material that you are talking here is a two-phase material. There is a reinforcement phase that gives the strength, stiffness, etc. There is a bonding phase, the chemical, that is the matrix. Matrix means the continuous phase. The reinforcement phase is discontinuous phase. Therefore, when it comes to the matrix, you enter into the field of chemistry. When you get into the reinforcement, it is more of physics. How the reinforcement is arranged, in what pattern, in what form, in what content, like fiber fraction, volume fraction. So I'll call that the reinforcement governed structure property relationship, and the matrix governed structure property relationship. So basically, reinforcement provides the strength and stiffness, as I said, and the matrix provides the bonding force and helps the load transfer among the fibers. When some of the fibers fail, the matrix automatically transfers the existing load onto the other fibers. It is like an equalizer, a normalizer. And finally, it also protects the fibers from various environments. But it doesn't mean that polymer is all weather proof and it has problems. I'm going to discuss it later. But basically, we are splitting the structure property relationship in two parts. Now, if you understand this structure property linkage in the polymer matrix composites, on the left side of the slide, you can say you have understood the polymer matrix. And once you understand the material, you can do wonderful things with this. Now, this is a standard slide, where the tensile stress is plotted against the strain, and the high strength carbon, high strength, high modulus aramide, and you have the S glass, you have the E glass. These are all the reinforcements. And the epoxy resin or polymer or plastic, they're all synonymous. So here we call it a matrix that binds these fibers together, either as a carbon or a aramid, or you can sometimes hybridize them depending on the requirements, multifunctional requirements. What I want to show in this is that the slope of the curve shows the modulus, the stiffness, and the point where it ends, that line, is a breaking load. If you see, the S-glass has the highest tensile strength, followed by the aramid, that is aromatic polyamide, the Kevlar fiber, what we call yellow color fiber. Then carbon, some carbon fail also less than that. But if you see the slope of the curve, carbon has the highest slope, followed by aramid, followed by S-glass. Therefore, we have to actually see in this slide, next slide, number 9. Okay, here the properties of reinforcement are summarized in a standard table. This is available everywhere. But what is important point is, if you come from top to the bottom of this table, material type on the left column, the carbon fibers score over others, followed by aromatic polyamide fiber, the Kevlar fiber, followed by glass fibers, and then the bottom rows, you have the aluminum alloy, titanium, mild steel, all metallic materials fall in the bottom line in terms of the mechanical properties, in terms of the density goes up as you go towards metals. But important point is, if you go through this slide very carefully, you get wonderful information for design purposes. But to the right side of the slide, I have summarized this table by showing you that I have ranked them according to the strength, stiffness, and specific values. So if your structure calls for maximum highest strength, for example, if you go to the back to the slide, the previous slide, you see the S-glass has the highest failure strength. Therefore, if the criteria of design of your structure is higher strength, then you go for S-glass, not E-glass. S-glass is a high-strength glass, higher silica content. Therefore, S-glass scores over the Kevlar, the aramid fiber, polymeric fiber, that scores over the carbon. If you go to the previous slide and the table, that comes up that way. But if you go to the stiffness, the resistance to bending, the slope of the curve, the previous slide, right? And again forward, present slide, the carbon scores over the Kevlar, that scores over the glass. And if you go to the specific values, that is, you divide the strength by the density of the fiber, you divide the stiffness by the density of the fiber. Fiber means the composite itself. So the glass fiber is a density of 2.54 grams per cc, and the carbon fiber is about 1.8, and the Kevlar fiber is around 1.4, 1.5. So the glass is heavier, carbon is lighter, Kevlar is lightest. So if you divide the strength or stiffness of the material, the fiber or the composite made out of it, by the composite density, then you can see that to the specific strength, that is sigma by rho, it will change the ranking. Kevlar outwits glass, S-glass outwits carbon. And if you go to the specific modulus, divide the modulus by the density, the carbon outwits the Kevlar, that outwits the glass. But one important observation that we should make here is, glass fiber is considered inferior to carbon and Kevlar in terms of modulus, but not necessarily in strength, and in density is higher. So in many critical aerospace structures, carbon is used extensively, Kevlar is used limitedly because it has some limitations, but glass is used in certain areas where carbon or Kevlar cannot be used, especially the carbon. That is the radar dome, which will be an electromagnetically transparent window. That means a carbon fiber acts like a metal layer reflects it. So carbon fiber is a taboo. Only glass fiber of a special grade, a quartz fiber or a L-glass, radon glass, you use it, where it gives a very good epsilon tan delta values. We have worked on this in radon engineering. Some of my colleagues in electromagnetics helped us. So the important message is that glass fiber, though it is looked down upon in some sense, there are some areas where you have only glass fiber, that is the radons. You can't use any other fiber. Similarly, if you go to the tennis racket use carbon fibers. Of course, in many aerospace structures you use it. So finally, the high performance composite is not just because the material is superior, but the application is also high-end application. So this is one of the messages we get from composites. Next slide shows number 10. The fiber placement patterns. Now you can place the fibers in a number of fashions. You can put them unidirectionally. You can put them bidirectionally by weaving them. Here, this left side figure shows the plain weave, the harness satin weave, 2x2 twill weave, 3x3 twill weave. These are all we use terminology that we get from the textile engineering, the science, textile science. So why we weave them fibers on the warp direction and web direction, that is the loom direction and the cross direction, shuttle direction. So if you weave them in different patterns, they give different flexibilities and pliabilities. That means if you are making large surface area structures, you have to use fabric type of reinforcement, and they can take the curvature very nicely. But again, if you go to some very streamlined shape, conical shape, like the nose radome of a fighter aircraft like Jaguar, you cannot use the flat fabrics like this because they don't take the double curvature, so it's conical especially. So you go to the contour woven, you weave the fiber in the form of a cone, and then like your cone, what you use for ice cream, like a cone, and then you put it on the mandrel and put a mold outside and inject the resin. So the fabrication technology also changes as per the form of the reinforcement. But important point here is that the continuous fiber composite CFCs are much stronger than the short fiber composites on the right side. Here we use it for different application, not necessarily for structural application, because the short fibers will not give you, they won't translate the strength of the fiber into the strength of the composite, because there is what is called a critical fiber length. That means the length of the fiber that is to be exceeded in the composite such that the fiber reinforcement efficiency is felt. There is a lot of theory, that means that will not go into details, but important point is we are only concentrating on the continuous fiber composites. The next slide, that is slide number 10, we see, slide number 11. The governing expressions for the continuous fiber composites and short fiber composites. At the top, you see the equation. This is called a rule of mixture for the modulus E. Modulus E of the composite is equal to the modulus of the matrix into volume fraction of the matrix plus an alpha term in the red color, and the modulus of the fiber into the volume fraction of the fiber. The important message here is that the composite property is the sum of the properties or contributions from the fiber side and the matrix side. This is called actually Voigt's rule of mixtures. That is, when you want to measure the property in the direction of the fiber, especially in unidirectional composite, this is a very useful equation a priori without going too deep into the complex, lengthy equations and theories. To calculate, if you have got known the property of the fiber and property of the matrix, you can a priori calculate the property of the composite as a whole. That gives, if you know the fiber property like modulus or strength and its volume fraction straight away. This can be applied for densities also and certain other parameters. But the important point here is that it is a function of, it increases as the volume fraction V term increases, the composite property increases. But you can see that the EM-VM, that is the modulus of the matrix, the modulus, the volume fraction of the matrix, actually they have negligible contribution. So the composite property E modulus or strength epsilon grossly is decided by EF-VF. So we can neglect for all practical purposes the contribution of the matrix as far as mechanical properties are concerned. But the role of matrix comes in a different way later. So in the bottom of the slide, short fiber composites, the same equation form is same, but you have a eta 0, eta L, which are the coefficients. The maximum value is 1. They vary as a fraction. They represent actually the alignment in fibers, short fiber composites, and also the critical fiber length, how much, whether it is exceeding or within that. So if it is a very small fibers, the eta 0, eta L will be very, very small fractions of 1. And the composite property EC you are going to get is much less than what you get for the continuous fiber composite given by the above equation. But if you are getting very good, as you increase the length and as you align the fibers more and more, you end up with the equation as given at the top. So this is just basically to appreciate a little bit theoretical aspect behind the polymer composite. Now, next slide, this slide number 12. It shows the slide on the left side is a plot of tensile strength on the y-axis versus the fiber weight fraction. Here, a glass polyester resin system is taken as an example. And right side, the similar pattern trend you see with respect to the Young's modulus on the y-axis and the fiber fraction on the x-axis. What does this tell us? Now, in the middle, I have shown 3 pictures. The random means the fibers are jigsaw, and next is bidirectional woven like we have seen earlier, and then unidirectional, where the fibers are all in one direction. For example, you want to design a aircraft structure, a wing, in which the spark caps have to be designed by unidirectional composites, especially carbon fiber, because the wings will only take the bending loads. So when it is in flight, the wings are pushed up because of the lift force, and the top spark cap goes into compression, bottom spark cap goes into tension. So in Hansa, we have done a lot of studies. So the bottom cap, the fibers can take tension easily, but the top cap, when it goes to compression can give it a buckling and shear forces within the layers. Therefore, we make a thicker top cap and a thinner bottom cap. But if you make it in metal, the problem is you have to machine a huge spark cap out of aluminum and from a big block. But in composites, the advantage is you can increase the thickness by adding layer by layer, 0.2 millimeter, 0.2. This is what people today call additive manufacturing technique or bottom-up approach. So you can see that when you go to the random fiber mate here, it gives only, because of the geometrical packing density is loose, it gives a maximum weight fraction of 0.4 if you see on the left curve, on the right curve. So because of the rule of mixtures, the volume fraction or weight fraction is limited to 0.4. You cannot increase its strength or modulus. Therefore, the modulus or strength in these two curves are limited only to the left bottom of the stress versus weight fraction curve. And if you go to the bidirectional fabric, you can pack more and more fibers in a given volume. Therefore, the geometrical packing density of the fibers in the volume of the composite is higher. Accordingly, you get higher strength and higher modulus. And if you go to the unidirectional fibers, you can imagine all your fingers you keep like this. You put the fingers very close, they're all beautifully maximum number of fingers. But if you keep the fingers away, they are loosely. So the volume fraction, weight fraction is less in a given volume. So if you go to the unidirectional fibers like tapes or fine rovings with which you can make filament wound shells, pressure vessels, etc., you can see that the maximum packing density gives rise to maximum weight and volume fraction. Therefore, accordingly, by the mixture rule, you get much higher mechanical properties like the strength and stiffness. This is a very important point where the fiber structure, its arrangement, also influences the composite mechanical property. This slide is very interesting. There's a standard slide available, but the important point is one thing to test the material in line with the fibers. Naturally, it gives maximum property. But if you test it, the transfers at 90 degrees to it, what happens? If it is unidirectional, in the transverse direction, you see the unique curve, strength versus loading angle. So it is maximum at 0 degree. That means along the fibers. It is least, it drops down so drastically when it go to the 90 degrees. That means you take your fingers like this, pull your fingers straight up. It can take load. But somebody pulls your fingers across, what happens? You can't hold them. What is holding there? Here it is only air, but in a composite, it is the matrix. So the binding matrix cannot resist loads. Therefore, in the transverse direction, the unidirectional fiber has a very, very weak strength. In fact, this is also true with human beings. Some people are straight, honest, upward. He doesn't bend. He is very, very strict, but somewhere he fails because he doesn't have that tolerance. So that's why the bidirectional composite, the BID, is very good in that sense. It has balanced properties on the x-axis direction, y direction, as you have seen in the previous slide. So at the extreme, it's 0 degrees. When you load it at 0 degrees along the warp direction fibers, you get some strength. And when you load it along the web direction, 90 degrees, you get the same strength. You see the U curve. It is here 0 and 90 is practically the same strength. And in between at 45, it falls down. So the strength of the composite, in addition to the direction in which it is laid, depending on that, it also depends on the direction in which you test it. Then the chopped strand fiber is very weak. It's just a flat curve. It is independent of which way you test it. You cut a piece in any direction, it gives the same property. That's what we call isotropy, like in metals, the homogeneous materials. So it is again another important thing is you must set the composite in the direction in which you have the fiber, or conversely, you must design the composite in such a way you place the fibers in the direction in which the load is applied in the structure when it is an actual service environment. So having said that, now we are now entering in a different field. That slide number 14, right? Hope it's running on okay. Nadarji?
Yes, sir. Going well.
Oh, thank you very much. I'm a
Very,
bit fast,
very
but,
clear audio, very clear video.
it's my voice also sometimes, I don't know. I have been practicing last 3 days. Okay, thank you.
You can have a break and take a glass of water if required.
No, I have water bottle here, so that is the
Okay.
next part. Oxygen ke paas, now there is oxygen also in this,
Yeah.
along with hydrogen. Okay, you are empowered me. There are enabling technologies. We are talking of enabling materials. That's right. So slide number 14, the paradigm shift, a big change from the reinforcement centric to matrix centric. This is my philosophy. All the time we say every fellow who scores the highest rank, we always say, or he is very talented, he dances well, he sings well, or she or he. People always look at that, oh, great. But we should not neglect the people who need the support. So here reinforcement is required, but reinforcement minus matrix has no meaning. It's like you have the fibers, you have got glass fibers, you take it, you can stretch it, but you cannot hold glass fibers and make rockets out of it. You have to have a binder matrix. So we'll see now we'll shift from the concept of reinforcement centric to matrix centric. That means the structure property relationship of a composite as referred to the contributions from the fiber or reinforcement. We have finished that part. Now we are going to the second part. The matrix governs structure property relationship. But the moment you go into the matrix, you go into a different arena. That is, you don't talk of strength or stiffness, you go into the lightly chemistry. So I'm not going to bore anybody with chemistry, except that I'll touch upon one or two aspects of it. But important thing is the polymer. So earlier, way back before Hermann Staudinger, at the bottom of the slide, 1974 Nobel laureate in polymer chemistry, everybody used to think the plastic, that is the phenol formaldehyde, bakelite, they're produced at that time for electrical applications and all that. But Bakeland has developed bakelite, one of the earliest thermoset polymers. But they used to call them plastic because some of them flow like metals, that is plastic flow. But everybody used to think plastic is nasty, plastic is cheap, because anything cheap is considered nasty. And it is smelly also sometimes. But what happened, Hermann Staudinger has taken this, and for years he has struggled to prove that they are macromolecules. They are not. Earlier, the colloidal chemists used to rule the roost, saying that anything that bulky, anything that is higher molecular weight is colloidal. That means it is something like a chapati dough, right? Or suspended in water. No, he said they're all macromolecules. As you see on the left side, it is like a monomer going into a big polymer, n number of molecules together, like a railway wagon and a huge railway train formed out of it. So, but he has to struggle to convince the people through his experiments, and he has done yeoman work. But for Staudinger, I think today we would have been talking about polymers. So then Flory is there, next, a bigger man, will not dilute solution. That's a different matter. So the important message is polymers are not nasty plastic. They are, our polymers, they are macromolecules, long chain molecules. The lengthier chain, the more the molecular weight, the higher the molecular weight, the higher the strength, stiffness, etc., etc. Now, on one side, we have the matrix for our new age application materials, what we are talking, the structural composites. On the right side, in 2000, Shirakawa, McDr, Mead, and Heeger, two of them US, and Shirakawa from a chemical engineer from Kyoto University or Tokyo University, Japan, and these other two from physicists and chemists. They all joined in a seminar. They found that Shirakawa did experiments with polyacetylene and showed that its conductivity, what you call electrical and thermal conductivity, is so high that it outwits even the copper. So we're surprised. Why? Because they found that normally plastics are insulating materials, but they have changed the perception. If you can intrinsically modify a polymer, taking the conjugated double bond polymers, that is alternate double and single bonds, like polyaniline, PANI we call it, and polypyrrole, and there are so many things, and dope it with certain special chemicals, it will start conducting. That is, it will reduce the band gap between the conduction band and valence bands. It's a big theory in conductive polymers. We have 2 PhDs also done in the FRP division when I was there. A wonderful So they have proved that polymers can be conducting, for which they got a Nobel Prize. So that Nobel Prize is something which we should aim in future. This is one of the wonderful things. Now, the polymer matrices. Broadly, now we come to the reality. They have thermoplastics on the left side, like metal. They have high viscosity, fairly high temperatures. Unless you heat them, they won't melt. And you flow them through the molds and then cool it. Then it becomes a set, rather solidified component. So injection molding is one of the standard techniques we know. Many things are made out of it. And volume of production is very high. But the important message is they are high viscosities because the melts are of high viscosity. And when you come to the fiber reinforced polymer mesh composites, one of the main criteria is that your fiber or fabric should be properly impregnated or wetted to its fully throughout the volume, so that the layer to layer bonding, fiber to fiber bonding is very well established in a composite after it is cured fully or solidified by the chemical reaction. So thermosets are very well placed in that sense because they are solidified only by a chemical reaction. That means they are available like liquid of different viscosities, and then you can easily impregnate the fibers or fabrics and then put it in a mold and press it. And you have to add what is called a hardener or a curing agent. That hardener, for epoxies, we use the term hardener. It's like putting a little curd in milk. Milk becomes curd. It's just an analogy, not one-to-one. So here the chemistry takes over. This is a chemical transformation. The thermoplastics are by physical change. But thermoplastics, as I said, are not really useful for very large structures, though there are thermoplastic reinforced with fibers, composites, but for small, complex shapes, injection molded. Here we are talking of thermosets, which are low viscosity materials. And of course, you cannot reprocess. Once it sets or cures, you can't do anything about it. So you must be careful about thermoset. So now we are going to directly, the workhorse material of modern composite. I put the horse head on top of it. This is that went into my head a decade or 2 decades back. So now the epoxy molecule, you can see that is called oxy-rain ring, CHOCH2. N times means there's a macromolecule. Now, if you put glass fiber in that, it becomes GFRP, glass fiber reinforced polymer, carbon fiber reinforced polymer, Kevlar, that is aramid is yellow color. I slightly put white and black and yellow to represent the glass, carbon, and aramid fibers. In fact, the interesting thing about Kevlar fiber is that we are all familiar with nylon. Nylon is actually, it is in New York and London. I don't know how many people wait. Two industries from New York and London brought out that a Carruthers experiments, nylon. But important thing here is that is an aliphatic group of polyamide. Now this aramid is aromatic group of polymeric fiber, and then the K in the Kevlar is the first letter of a lady who has actually worked or invented it as a chemist of the DuPont. The DuPont trade name is Kevlar. So all the ladies should be happy. One of the greatest contributions to composite comes from a lady. That is, she is some Stephanie, some Kevlar or something like that. Okay. Anyway, now if you see the bottom curve in the slide, stress strain, if you see the carbon fiber, that black stuff, it has the highest modulus. The slope of the curve is very high. When you go to the yellow curve, that is the Kevlar, which the slope is less, therefore Kevlar modulus is less. In fact, carbon fiber modulus ranges from somewhere 250 to 400, 500 high modulus carbon fibers, and Kevlar is around 120, 140. And glass fiber, if you take as glass, is about 80 GPa. 80 GPa versus Kevlar 120 versus carbon about 200 to 500. So when you want extremely stiff and dimensionally very rigid structures, you go to Kevlar. When you want only higher strength, you go to glass. In between is Kevlar, but Kevlar has certain limitations we'll see later. But the point I want to make in this slide is that the workhorse material for modern composites, the matrix is epoxide or araldite. They use it crudely. That is, you take a liquid resin and then you add the hardener in a different proportion decided by the chemistry. That's what we call a stoichiometry. Now, the interesting aspect is the matrix governed parameters. There are two things. One is what is desirable. We come to one new important term, glass transition temperature, TG. This might be familiar to people who are in the field of composite science or engineering. We'll talk about it later. And moisture absorption, it should be as low as possible. That's why arrow is down. And the toughness should be T, the green arrow, as high as possible, because the layer-to-layer bonding takes place by the polymeric thermoset polymeric film. And if there is a defect in the plastic film, that should not propagate. So the toughness of the matrix is very important for getting very highly damaged tolerant structures. So, but the desirability is that you should have a high glass strength temperature, because glass strength temperature is a measure of the service temperature limit of the part which you are making out of this composite. Therefore, that is where the matrix enters into the picture. Its importance also comes out. I'll show you in the next few slides. But the reality is that the glass transition temperature TG goes up as you cross-link the molecule more and more with different hardness. Therefore, you get higher and higher service temperature for the product. But the moisture is a culprit. It pulls it down. That's why I call it a push-pull mechanism, like a push-pull train. But it's not a push-pull train from Bangalore to Mysore. All the way, it pushes from behind and it pulls from, because when you go from Bangalore to Mysore, you go down. Mysore to Bangalore, you go up. So, but here, one pushes it up, one pulls it down. So how do you manage? That is very interesting. So if you want to increase the TG, you must make sure the moisture absorption is very, very little. We'll see the importance of moisture absorption in the next few slides. But on the right side, you have the TG, yellow line. TG you can increase, but the toughness goes down. Why? Because TG is measured by the degree of cross-linking. The more the cross-linking in the polymer molecule, the higher the glass transition temperature. Therefore, you get a composite with a higher service temperature limit. But because of the degree of cross-linking, the brittleness increases. It's a three-dimensional cross-linking. So as the brittleness increases, the toughness goes down. So what they call, you cannot eat the cake and eat it too. What we have to do is, so two of my colleagues, in fact, I cannot put all the names here. They're all wonderful people. And with that team name there, you can make wonders in the world, I can say. Though I have retired almost in 2007. So that is this level of scientific and technological, competence we established thanks to the supports we got, right? So the TG and TF are at loggerheads. So one of my colleagues has actually worked on high temperature polyimides. So modify with epoxies. It is what's called interpenetrating network polymers, IPN. That's a very good solution where you can increase the TG at the same time, not sacrificing too much on TF. Okay. Now, what is this TG? On the right side, it is we call thermodynamically or fundamentally, if you plot the specific volume versus the temperature, that means if you take a thermoset plastic, which is a solid glassy state, amorphous, you keep on heating it. When it crosses that characteristic TG, if you can see that encircled in the red, it starts suddenly changing. But if you actually specific volume is inverse of density. If you plot density, the curve reverses. That means at TG, it nosedives. That means density goes up. And the mechanical property, if you see on the left side, this is a dynamic mechanical curve. The storage modulus. See, polymers are viscoelastic. You have storage modulus, you have loss modulus. Storage modulus speaks of the elastic component, and loss modulus, the viscous component. So the storage modulus, which is a measure of the stiffness of the material, nosedives, you can see from 2 to 3 glass tank temperature range, it suddenly goes down. So the important message here is that if you make a cast structure with a matrix whose glass tank temperature is close to the service temperature of the actual component in flight, for example, then what happens? The whole modulus, the stiffness goes down, and your aircraft becomes a rubber-like, and many things will happen. So the importance of the matrix chemical structure and the glass to rubber transition temperature is very, very critical. So we have done a lot of studies in Hansa on this. Hansa taught us a lot of stories. Now, putting in equation, the glass transition temperature TG versus the composite performance, it tells us how to choose a matrix. A thumb rule, the TG dry, that means the as cured, as solidified polymer matrix composite, the glass transition temperature measured by thermal analysis techniques should be at least 60 degrees above the service temperature. That means if your service temperature, for example, Hansa, white painted Hansa by Kirchhoff's laws of radiation, they have found that the white body, the maximum skin temperature when the ambient is about 50 or 60 degrees, maximum aircraft seats. So it is about 60, but I need to have glass transition temperature matrix 60 plus 60. because that extra 60 is to account for the drop in the TG. We have seen the previous curve. TG comes down with moisture absorption. Moisture absorption is to be reduced, but cannot be avoided total, because when a flight vehicle or a vehicle in the open environment performs so many years, it will pick up some moisture. So that moisture is bringing down the TG, and your ambient temperature goes above TG, then is a disaster, whether aircraft or even a ground-based radar. Therefore, that margin of 60 degrees should be there, and there are processing variables. I make a component using a process sheet, same material. You make it, but certainly they're bound to be different because the composites are heterogeneous, multi-phase materials. So we cannot establish exactly, repeat it. Even in twins, we see there are differences. Okay. Anyway, now there are two important stories here to connect us to the one is adventure, the other is a disaster, the other is a disaster converted into a success. The first story is about the next slide. See the myth and reality about TG and MA. So slide number 22. See here, you could see on the top, of course, the ape man was wondering, asking himself, can I not fly like the birds? So that gave the impetus to the today's aircraft, slowly. The bottom curve, I don't know if you have to expand the slide. You see one man flying on top, another person falling down, if it is very clear from the slide. So the story is that Icarus and is a father and Daedalus' son. It's a Greek myth story. They are once held captive in an enemy's prison, and every day they are taken out, and after doing hard work, they are brought back and put in the cell. They are given a candle and a matchstick to use it in the night to read some book or something. That is the humanity they have at least. So the father one day saw they are there for years. He said, look, son, one day when we go, we'll pick up some feathers and stealthily we'll bring them in. And nights we will not sleep, we will not use the candle. We will bond the feathers with the wax as a matrix and make two sets of wings, one larger wing set for me and one small for you. And then one day when we go out, we'll hide them in the aprons, go out to the end of the cliff, and when nobody is watching out, just open our wings and jump out and wave the wings and then escape. Beautiful plan. And then the son and father get ready, and then one day they go, and before they jump off the cliff, he says, my dear son, don't go too high. If you flap the wings too much, you will go high and high. The wax will melt because you go closer to the sun. And the son, yes, daddy, okay. After he jumps, he gets excited. Just by too much of swinging his wings, he goes up and down because he gets very good lift. Then aerodynamics starts working. And finally, the wax melts. And alas, what happens, that means there the wax melts. Here the glass junction temperature, because the thermoset is something like the wax melting. If you don't design your matrix much above the service temperature, that is TG plus 60, a similar thing can happen. And with moisture absorption, it is disastrous. Now we'll see next slide. This is a beautiful slide. 1982, the Columbia Space Shuttle carrying our three great astronauts. Neil Armstrong, Edwin, there's one Edwin, and then Mike Collins, 90, he passed away at the age of 90. Okay, now these three people were shot into the lunar orbit. Now the space shuttle, after it entered the space, if you can read it, it started twisting strangely in flight. Then they were wondering, because the ground control people are here and spacecraft is somewhere, kilometers or millions or thousands of kilometers away. Therefore, then they suddenly thought, oh, there must be a problem of moisture absorption because the spacecraft was kept outside in the open. There was a heavy rain that lashed for a few hours, and that is covered in the front by the porous carbon-carbon heat shield tiles. So they are porous. So moisture will have what it did. Therefore, then the flight control, director one, Harold Doughton. This I picked up on the Deccan Herald local newspaper, 29 June 1982, ahead of my submission of thesis in 1983 on moisture absorption, luckily for me. Then immediately they think, if the moisture absorption theory is correct, then by maneuvering it from the ground, spending some extra energy, they turned the heat shield toward the sun for 10 hours and evaporated the moisture because the sun heat will evaporate it. And they calculated some mental calculus they made. Finally, the spacecraft started behaving properly. That means this has proved that later the reports came that it was a successful mission. So we have a partnership in the putting the 3 men on lunar space. That's what I feel. And I was fortunate just to pick up the news from the Deccan Herald and put it in my thesis 1983. So noise absorption is a big culprit. If you don't address it, we are in trouble. If you address it, it is a good friendly thing. So now we'll come to the glass transition temperature requirements for the matrices we choose for the composite. Let it be any fiber. The fiber doesn't come into play here. Its strength, stiffness are already embedded, but their retention at higher surface temperature environment like heat and humidity or moisture is governed by the matrix. That's what I wanted to emphasize in this 2 slide. And now, if you go to the subsonic aircraft, we use what is called bifunctional epoxies. That is, you will have 2 active groups through which the cross-linking takes place, like a dodecyl glyceryl ether of bisphenol A, DGBA, we call it. It has 2, like one person with 2 arms stretched. He can link to 2 more people, 2 more like that. Now, the maximum TG you can get is 120 degrees for a very special epoxy which you have formulated. And then by a special post-curing technique, we pushed up its room temperature TG to as high as 115, 120 as measured by the dynamic mechanical spectrometer, etc. And this is used in ANSA. ANSA is a subsonic trainer aircraft. Now, if you go to the transonic and supersonic aircraft, because they travel at higher speed due to aerodynamic heating, because skin gets hotter, therefore the surface temperature of the aircraft will go to something like 100 or 100 plus minus. Therefore, you have to have a glass transition temperature of 160. Then you go to what is called multifunctional epoxy with toughness and all. That's what they're doing in LCA or Tejas in that class of materials. Now, if you go to the higher and higher temperatures like air engine parts, you encounter much higher temperatures because of the heating. You go to what's called bismaleimide cyanide esters. Now, there the skin temperatures will be as high as 20. Therefore, you go to a matrix like bismaleimide cyanide ester of transition temperatures 250 to 300. So this is the meaning of the glass transition temperature, the matrix dominated or matrix contribution to the composite properties. Now I'll next go to the 26th slide, where we will talk a little bit about design. I'm not a designer, not an analyst, but because of my long and strong association with a lot of my colleagues who are experts, world-class experts, like a mechanical design, machine design, finite element analysis, and CFD, and engineering services, and my own team of chemists, engineers, and wonderful technical staff, and masters in the art of fabricating things as we want with utmost care. So we had put together the R&D under one roof, that is FRP division I left back before I came out after superannuation. Now here, if you come to this picture here, the extreme left, you have a lamina. Lamina means a single layer. And next is a laminate, number of lamina put together like a layer structure, and then with fibers in different directions. That is single layer, unidirectional layers put in different direction to get different properties, multi-directional properties when you make a component of it. And that is converted into a shape. The third figure shows either the aircraft wing or a flap or aileron, etc., etc. So the data that we generate at the laminate level in the middle. But the design analysis people want a single layer property. That means the property of the lamina goes into the design of the structures, actual shape, and the property of the laminate gives you a lot of design data from which you develop what is called design allowables. So in the next few slides, we'll see that. These are all the various test specimens for generating mechanical property data. So here you can see on the top, these are only schematic, and you have got the ASTM standards, ISO standard, German DIN standards, and military standards, MIL also, when you make, especially the defense and military, flying vehicles and that sort of that. So tensile strength, if you measure along the fiber longitudinal tensile, it gives maximum because we tested in the fiber direction. But you also use it in the transfer direction, transverse tensile. Similarly, you have compression, longitudinal compression, and transverse tension, the reverse of the tension. And there are other tests, but the bottom, you have what is called in-plane shear. That is, you take a 0 and 90 degrees fabric and cut it at 45 degrees and pull it. So you are testing actually the shear, matrix shear between the fibers. That is very important for assessing the damage tolerance of the structure. And also the compression is very important, especially as I said, the aircraft wing spar. The top goes into compression, bottom goes into tension in the full flight when the aircraft is under lift force. Therefore, then tensile strength anyway goes into the composite structure when it is undergoing bending or what you call tension, fuse tension. So these three properties have to be generated in vast number of specimens. In metals, actually, 3 or 5 are okay. That is approved because it is highly homogeneous and repeatable. But in composites, you have to at least do for every batch 15 or 20 or sometimes 30, and the variability will be so much that the top 5 or 10 and bottom 5 or 10, that means the highest values and lowest values you neglect, and you take only the middle 7 or 8 values closest to one another within certain tolerance, and then take an arithmetic average, and then do a statistical average on a large number of batches of specimens. In fact, it is not a hype if I say we have tested hundreds or thousands and thousands of composite specimens only to generate one single property, one allowable, a tensile allowable, or whatever it is. So the important point is now you generate the data. Now we go to the factor of safety. So design concerns for aircraft composite. Design allowables are 2 types: the A basis allowables, the B basis allowable. What is A basis allowable? If you take 100 specimens, 99% of them, 99 out of 100 should fail with a 90% confidence. And they are used in primary structures, very stringent. That means like spars, attachment points, critical bulkheads. And if there is a failure takes place, the whole aircraft fails and the safety is jeopardized. The basis allowables are, instead of 99 out of 100, 95 need to be passed within at all 90% confidence limits. And such design data, B basis allowables, are used in wing skins, control surfaces, which are secondary. Sometimes the failure of a wing skin or control surface doesn't automatically land the aircraft into danger. There'll be enough time. Not that it should happen anyway. So these are for A basis, you have to test a large population of specimens. So for B basis, you have to test a limited. But when you are making aircraft, when you are going to produce a number of them, you cannot do this once you are established. You only do a subset, batch to batch you do it, so that you don't do it for everything. In fact, even when you make the radome for Doppler weather radar, ISTRAC, the 12.88 meter diameter, which has a 666 panels for the Mark II version. And then there are about 5,000 bolts or so. So stainless steel. For our ISRO will insisted at least for 50 or 100 bolts, you have to again test it. And again send it to the materials lab for this chemical, composition. So much care we have taken, because the radome is a huge structure protecting. The radome may cost 1 crore, but it protects the radar inside, which costs 10 crores, 20 crores, 30 crores. So that is the importance of testing number of specimens, and it is much larger in case of composite. So the factors of safety, if you say the design ultimate load, that means the load at which actually test the structure, take it to the limits, is about 1.5 times the DLL, that is called design limit load. That means in case of metallic or brittle materials, metallic structures, they initially follow the Hookean, elastic curve, and then slowly they yield, that is sigma y, what you call it. That yield point, DLL, you multiply it by 1.5, so that at that you test it. But when it comes to the composites, like polymer fiber composites, you use something like a 2.25. That means here the design limit load is a failure. That is, it goes like a brittle material, straight line, it cracks, because composites are brittle. They don't deform by plastic deformation. They don't have a yield. So that DLL, you multiply by sometimes 2, sometimes 2.25, because our Hamsa was made manually at that time by hand layer. And with a lot of care, we use a higher factor of safety to be on the safe side, because process variability will be there. But today, we have established what is called just-in-time pre-preg, JIPREG machine. Anybody can go to NAL that was established in 2006 when I left after 10 years of struggle to get 1 crore of rupees just for it. And today, everybody is looking at it. I'm very happy about it. That is a different matter. So the factor of safety for the composite material is about 2 times or 2 to 2.5 times, depending on the type of material and the fabrication method, the mechanized or manual, the quality control, plus the other variability from process to process. So that is but all these design allowables come from the vast data of experimental data on the laminates, as you have seen in the previous. Now, we'll go to a bit fast on the manufacturing side. And I'm fond of using a trinity, like even Bhagavad Gita, Lord Krishna says, everywhere Triguna, he says Sattva, Sattva, Rajas, Tamo, 3. But the trinity, like a Ganga, Yamuna, Saraswati, everywhere it is 3, 3, 3, like a Trinetra in a Lord Shiva. So everywhere you have 3. What is this 3 in this? So it prompted me to see what are the 3 important steps in the composite manufacture that takes the physics engineering through chemistry into the practical product. Now here you say this is schematic. The first one is you take the fibers and dip it in the resin or soak it. I'm fond of calling it soak. Then you shape it in a mold. This is only what you call pictorial. That mold can be any shape depending on the actual shape of the component. Then set it. Setting means curing and hardening. So I am fond of using the term soak, shape, and set. So, but in the setting, there is a chemical cross-linking, which I'm going to show you next, where it completely becomes a 3-dimensional network of molecule after you add the hardener and resin, impregnate the fibers and mold it into a mold like this and apply vacuum or pressure, whatever it is, and it cures. And it cures. And if you use a medium temperature hardener and a bifunctional epoxy, you get a lower glass tension like 120, which you use in Hamsa. But if you go to higher, what you call multi-functional epoxy with more active groups in that, and cure it with an aromatic amine, with a higher order amine, then you get a higher glass tension like 160 or and above. Therefore, the service temperature limits are governed by the method of curing, by the choice of the functionality of the matrix. I can show you in the next one. See here, this is a beautiful picture. I have actually animated versions. Unfortunately, I could not put it in this. So on the top side, you have the epoxy ring. Now we add what is called RNH2. That is the primary amine. R can be anything, any group. So NH2 is the amine. Now it opens the epoxy ring. As you see, the arrow you take down. So CHOCH2 becomes CH2OH. One hydrogen from NH2 comes here and opens it. And it becomes secondary amine RNH. Then further reaction takes place. Another hydrogen also lost. Another OH is created. So it takes back the different dimensions at the same time, and you get a 3-dimensional cross-linked network molecule. That's what we call setting, thermo setting. It sets by heat, and sometimes no heat also. And then you see on the left side, a lot of molecular chain beautifully, in fact, they move like the earthworms you put in a glass, they'll be just sleeping. But if you heat it, they start moving really. So here they have the degree of freedom. But once they're cured with a hardener, they completely lose their degrees of freedom. They get sick. And imagine all the fibers around that, the glass has shrunk onto the matrix because of the curing. And that is what it means. That is pure reaction. That is the matrix chemistry. Now, applications of polymer matrix components. Here, I'm not going to too many. I'm not going to, because they're vast, so many products you can show. But what is important is, broadly, you divide the applications into high volume applications and high-end applications. The high volume is where the population, a lot of people use, thousands and millions of people, like automobiles, like many utility items, and so many things, like automobiles, chemical industries, domestic appliances, we know everywhere it is used, and entertainment, industrial, sports. Today, everybody is using carbon fiber rackets. Now, the carbon fiber rackets are outfitted to wooden fiber and aluminum rackets today. So anybody plays, an ordinary fellow like me plays with a carbon fiber racket against a champion holding a wooden racket, I can take one game at least, because that is the power of composites, like transport vehicles. But there is a large volume consumption. But there, the cost is important, because otherwise you won't break even. because the volume of production is so high. Because quality is important. There is some premium on that. But when you go to the high-end applications like aerospace, biomedical, something like human implants, and meteorological electronics, communications like radomes, and so many, you have to have a very high quality added to that, reliability and repeatability of the property or performance, and finally, safety is utmost important, a spacecraft or an aircraft. Therefore, here the high-end applications demand the cost will not come into picture to start with. Later, the cost may come, but if you give importance only to cost, you will be losing on other parameters. Therefore, but imagine an aircraft carrying 600 or 800 like a A380. It is also a high volume application only. You are taking 800 people in one shot. So that is also important. But broadly speaking, it is a cost-centric and quality-centric. Now, this is the internet downloaded. You can make automobiles, you can make large buses, transport vehicles, military trucks, and then even beaches are made. I think in India, we are to catch up. Though in defense sector, they are making selectively in some points. And then sports, and you have got marine, and you have also artificial implant, the joints, knee joints, etc. And the hockey stick there. Of course, helmet are most. In fact, when you talk of damage tolerance, I get one beautiful, that if you have a metal helmet, in case of a impact, there will be a dent because it deformed by plastic deformation. And that metal dent will form a dent in the skull. That's why we don't use metal helmets anymore. So the fiberglass helmets, which are layered structures, in case of impact, they get delayed, delaminated, and the energy is absorbed by delamination. Therefore, the skull is safe. That is, in fact, long back I read somewhere in South Africa, there are home-built aircraft they used to make in composites, and they used to fly and then just crash onto the ground and come out safely. It was a fact, but I don't have the the papers or literature on that. Some agent, salesman came and showed me some pictures of it long ago. So damage tolerance is a very, very important contribution of the polymer composites. Now, let us just take a small look at the emerging trends in composites. See, we wouldn't have come from the primitive age to today unless, somebody or the other went on inventing, and then bringing new materials, new process, new technologies. Nobody is satisfied. That is what the passion is. Passion drives it forward. Therefore, here, new materials. Now we are having polyamides, with a maximum of 300 degrees glass tension. You can use it till 200, 250. What if I have a matrix material, which can give me 500, 600 glass tension temperature? Can't I make it? In fact, I posed the question, many of the pure science people, some of my colleagues also, I'm sure they are aware of it. So ultra high TG matrices. Again, you don't go into metals, then you end up with high densities and corrosion problems. The nanostructured, and today we are talking of carbon nanotubes. The carbon nanotubes are very fine, small. They are looking like powders. And it is to the credit of in EZIMA laboratories. A gentleman as in electron microscopy first he found, and Professor Ajay now in Rice University is working in the Nobel laureate seat. He sits there, and he has been responsible in productionization of carbon nanotubes in large scale structures. But the important point is, if you can make carbon nanotubes in that small powder form, they won't give us reinforcement. They have to be far lengthier, like cross the critical fiber lengths. So if you can make carbon nanotubes into ropes and long fibers like the glass fiber or carbon, you can make your aircraft or spacecraft a lot lighter. And because carbon nanotubes modulus is 1 terapascal, that is 1000 gigapascal. The best of carbon fibers today, lengthy fibers, are something like that. It ranges from 250 to 400, 500 modulus, or 600 at best, but they're very expensive, not accessible to everyone. But if you only can put some more research into carbon nanotubes and make long carbon nanotubes with 1000 gigapascals, 1 terapascal, and even the tensile strength is expressed in gigapascals, whereas tensile strength of carbon, glass, etc. are expressed only in megapascal. So there are a lot of advantages. And carbon nanotubes, there are varieties. You can make them conductive carbon nanotubes, insulating or semiconducting by changing the inside the chemistry, the arrangement of that, there are different structures anyway. Then methods, cost-effective technologies, rapid molding. Now, the thermoplastics advantage is you can mold number of pieces at a given time. But thermosets, you have to give the time, 2 hours, 3 hours, 5 hours, sometimes days, the curing and like a cement concrete, you have to allow enough time. Earlier, we used to leave 21 days before, build further structures for curing. But today, fast curing cements have come. Within 1 or 2 days, again, you can construct superstructures. A lot of research has gone into that also. So we have to have very fast. One is high performance matrices and modified matrices, CAT modified. And then you have the methods to convert them faster into product shapes by molding technologies. One of them is you make the pre-formed shapes, put it in the mold and inject the resin, and fast curing at the same time, not losing the property, not developing the brittleness, because fast curing is always brings in the brittleness and residual stresses. So there are methods, and then that is what's called out of autoclave techniques. And at NIL, we have established what is called just-in-time prepregs. So I have coined the word GPregs. It has caught up now, the imagination of many people today. The just-in-time prepregs means you take the glass fabric on, release it from this mandrel, and then from other side, you take the resin as a thin film on a plastic film, and then bring them together in a calendering roll and push it through. Then the resin film gets transferred into the fabric, and the advantage is it doesn't distort the weave pattern, the weave structure. The satin remains satin, the plain remains plain. Therefore, without weave distortion, you can impregnate, wet the fabric by resin film. It's called resin film transfer technique. And then you can control the fiber matrix ratio very well. 65%, 75% of by volume of fiber under matrix. Therefore, you get very high mechanical properties. It is reproducible. There is a computer control machine. It will dose the resin exactly in the quantity. There is a doctor's blade which will swipe it, make it a thin film, and it is proved in 2007. It is almost 14 years it has been working. Many of the radomes are made of it. Now I understand for the new generation, HAMSA, what they are doing now, they are using this machine. So it is conceived in somewhere in 1998 and realized in 2006, and its real application is coming today. That means research is long-term, results will come. So research should not end up just as a, what I call, fashion. Now, I mentioned in the previous slide number 33, fiber metal laminate. What is this? FML. Now we are trying to get away from metals because they are heavy, they are corrosion resistant, they are prone to crack like aluminum. But somebody in Delft University, my God, in Holland, about 20-25 years back, they first made what is called Aral. Aral is aromatic, like Kevlar with glass. But Kevlar has a problem. It has a weak compression strength. So they made it in some military aircraft. It failed. Then somebody started with glass fiber. Now glass comes calling now. Glass fiber with epoxy, in between aluminum, thin aluminum foil. So you have alternate layers of, you can see in this structure, A38 aircraft on top, I have put it separately. You have one layer of aluminum, you have one layer of glass epoxy, aluminum, glass epoxy, aluminum. Put number of layers, autoclave, bond it, and then now you see because of aluminum, it will drape or it will bend like a sheet metal. You can work it like a sheet metal, whereas the thermoset composite, once you set it, you cannot bend it. And you have to bend it and then mold it. But here, the fiber metal laminates are like sheet metal. You can bend it and shape it to anything. A maximum portion of the upper fuselage of A38 aircraft, which weighs 650 tons now. That is so many thousands of kgs. And with a maximum passenger capacity of 800, when it is all J class, but it is 555 in 3 tier, the J class, the business class, the executive class. And it has a range of 15,000 kilometers. It's a maximum operating speed of 0.89 Mach number. It incorporates what is called the GLARE, glass reinforced aluminum. This is the result of a PhD of a student from Holland, mind you. Have you done a PhD where such a material has been introduced in any of the structures? Now this aircraft is carrying, it is a direct success, A38, well, Airbus. Now I'm coming to the last few slides of my own philosophy here of this presenter, that is myself, is that science pursued with a passion, because I do what I want. It's up to others to get what they want. It's fine. But pure research in its pristine form is very important, because not all the people can go to the fundamentals and study the principles of science. But that mere passion, if it ends up in research, publication of papers, guiding and all sorts of things, you get a lot of laurels and awards, but it becomes research open-ended, it diverges. But if you can add passion, a bit of purpose, societal, of course, it becomes research application oriented. Madhurji, are you able to see the slide now?
Yes.
Okay, thank you. Once in a while I interrupted, otherwise you had to do it for me, otherwise I missed it. So then if you add engineering to that, your mechanical, electrical, everything comes into picture. Even electromagnetic steps in when it comes to radome. In radome itself, I can talk days and days. We have wonderful work at NAL, So if you add engineering to that, now it is science.
It is not moving. I think there is no other slide other than this. This may be the last one.
Sir? Acha. So now we end up with a product. So what is research open-ended becomes a technology with end product, but it has science, engineering, and technology. I call them again the Ganga, Yamuna, Saraswati. Sometimes engineering is not same. Technology, you make a process sheet to get the material, blindly follow the procedure, you get it. And science, of course, it is a backing to that. But science, engineering, technology, only when they are properly blended, that is where I think, a country where we are a lot, though there are many people who are striving for it. And it is a multidisciplinary area, so nobody should have any egos. We should all work together, and that is what we learned in the radome development. Thanks to some of our colleagues from ISRO who gave us challenging tasks, and many people, HAL, ISRO, IAF, Indian Navy, everybody whose problems was, whenever they are from, they used to come to us. And our director used to say, you do it, then only we'll ask for money. And that was a wonderful year of golden period of our achievements. The last slide. Now we are talking about it on the Youth Technology Day. So I'm first of all very, very
last slide is this aircraft one, or one more slide is there after that?
After that, aircraft, thoda suspense. Abhi.
Okay.
ऐसा आसान से ठिकाना नहीं जाता. I don't know whether I'm exceeding the time. How much time I took, I don't know.
No, still time is there, you can take. No problem.
And another 5 minutes, maximum 3 minutes. Okay. Now, here I want to, this is my message because it's the 11th May Technology Day 1998. NAL has flown successfully the Hansa aircraft, all composite, 2-seater trainer aircraft carrying 1 instructor and 1 trainee, right, into the sky within an all of weight, that is with 2 people, passengers inside, each allowed up to a maximum of 75 kgs. 750 kilograms, fully laden all of weight when it takes off should be, they call it MTW, maximum takeoff weight. Within 650, that is as per the JAR VLA specifications for light aircraft. JAR VLA means Joint Airworthiness Requirement for very light airplanes. And we had to struggle out of almost 10-12 years to reduce the weight to get the approval of the DGCA final. So that lot of work, it's a huge team ANSA and NAL work, and I cannot single out any person. I was fortunate to be somewhere in that long chain of team, like a polymer molecule. I am one of the monomers there. That's my contribution. So the R&D issues that I addressed, some of them which I read out in the previous slides, are all there now in this. In Hansa has taught us a wonderful, complete picture about polymers and composites. So the materials, right from storage, how to store them, they should not lose their shelf life items like medicines today. So the processing, fabrication, and multi-level testing to establish, design the data and design allowables, and finally also see whether what you have put into the design is realized in the actual structure. So material testing, specimen level, travel cooper level, feature component level, semi-structural level, assembly level, full-scale testing level in the static testing or structures division, structures integrity division. So the characterization, normally testing and characterization mix it up, but characterization is different, testing is different. So characterization is the fibers, the matrices, the hardness, you get into chemistry and pastes, adhesives, foams, which are used as the sandwich construction in the wing skins and fuselage skins. And then through thermal, hydrothermal is moisture and temperature effect. And I have one student with that, which all my PhD thesis in 1983. And later one of my colleagues also did a lot of work. In fact, her hydrothermal research on not only in water, but in other oil and other environments, fluid environment. And the thesis became a rallying point for us to ask DGCA to certify our room temperature cured epoxy for the Hamsa class aircraft. Because, but for that work, we wouldn't have been able to certify our aircraft. They said, you go to autoclave, you go to high temperature matrices. No, but we have done it in a very humble way. And that aircraft is proved and certified. Now, finally, the DGCA has certified in 2000, Directorate General of Civil Aviation, as per the JARVELI regulation. And Hansa was acclaimed as the most researched and certified all-composite aircraft trainer in its class. This is CSR newsletter, I think it came up on last slide. So now technology in flight, that is my font slide. So you can make a technology. Now you have to show it in flying. The proof of the pudding is in eating it, the kid. Now you see, I hope it will work now.
Yes, technology lasts to the aircraft. Hansa is there.
Sound, I don't have a sound here. I have only a fan behind me.
No, we are hearing you, sir.
Yeah.
Aur ek baar. Once more.
Yes.
Kya ho gaya?
No, we are seeing
Yeah.
Hansa.
You are able to fly.
Hansa moving. That
Hansa
noise
in
is
flight.
coming.
Now, do you have a sound there? No.
Sound is there, something in background, but I don't know whether it is from the slide or.
If it is bad, I'm not able to. But it is flying, I'm happy. Sometimes it refuses to fly. It is shy of flying.
No, sir. It is whether it is a video.
A
I would
video.
say it is a movie, a small movie, sir.
Yeah, it's a movie only. That day when it flew in 1998
Okay.
from HAL ground.
So
Yeah.
we are getting only photo of that, though.
Yeah,
movie
only
is not-
picture is coming. Sir.
In fact, today I don't have any hesitation to say I have whistled actually my childhood habit. You know, when my
No, it's
director
okay, sir.
said-
It is okay. We can
says,
understand.
"Oh, normally he's very serious. He with a smile, he
Yeah,
patted
yeah,
me."
yeah.
So that sums up my talk on what do you call the first slide. If you go back,
You want first slide?
first slide. Okay,
Okay.
that's all. So we are back to square. We have landed on the ground. So
Yeah. The
so
first
this
slide,
is-
title slide has come.
Hansa is the most appropriate product that I could show on this day. And I hope you all appreciate my presentation. And I thank you all for your patience. And I don't know if there is an interactive section, I don't mind, but I'm not seeing it. But I would urge that if they have any questions or clarifications, they have my email ID. You can do that. They can all send the questions. Is it okay?
Yes, sir. We can ask some of the questions if time is there. Chintamani,
Yeah.
we can take some questions.
But I don't know how many have participated. I have no idea because there's no video.
First of all, thank you very much, sir, for giving us in-depth view of the composite materials. And
Yeah.
I'm sure all participants who are watching us from YouTube and part of the Zoom meeting, they have enjoyed such in-depth view. Session is open now for questions. Are there any questions, Hari, from YouTube?
Please ask them to speak a little louder. Because my speaker is a little low.
Chintamani sir, Hari sir has put a couple of questions up in the chat box.
Okay.
Okay,
Can you?
Hari.
Yeah.
Uh,
Yeah, so there is question from Mr. Mahadev Lokhande. Have you come across where small sized anti-friction bearings are made with 3D printing? If yes,
That is 3D printing question.
No,
Anti-friction-
that question is not valid here.
That is 3D printing question, sir. Previous
No,
lecture.
So, first of all, you asked me a question which is very, as Madhuri said, slightly out of my syllabus. But the thing is, anti-friction, we also worked out long back, but I lost track of it. you can go to particulate composites, okay? And you have carbon-carbon brakes, which are used in aircraft. So the conventional asbestos, based brakes have been replaced by non-asbestos, compositions. But you have to go to particulate composite. There is a lot of development has taken place, but I cannot answer that question a priori.
Sir,
But
can
you
I?
can use 1 minute. You can use a lot of ceramic fillers like silicon carbide, which is highly abrasion resistant, into epoxy composites, and make particulate composites, and make the small components and test it for the friction and wear characteristics. Yes, in fact, we have also studied it, wear and friction of particulate field composites. Yeah.
So perhaps sir, Ashok sir wants to add something. Ashok sir, please.
I'm Ashok Shukla, sir. Rao, sir.
Oh,
It was a very enlightening talk by you, and it was fantastic. I'm sure that everyone enjoyed it and learned a lot out of it. But while listening to you, sir, the 1 or 2 points emerged in my mind. I thought I should put across and take some clarification from the expert.
Sure, bully.
Sir, one thing you talked about design margins or design safety margin we take for designing of the components or the complete machine, like for aircrafts or aeronautical applications, the composites. As I remember, 99% samples for mechanical strength must pass.
Yeah.
And for non-aeronautical, 95% is allowed.
I don't say non-aeronautical, aeronautical only, but secondary structures.
Secondary structures. Okay.
Yeah.
No, my point here is that something flashed in my mind, whether during testing, this NDT, non-destructive testing, can be of help here, and it can, without having a destructive test, by cutting this samples, dumbbell-shaped samples and straight rectangular samples, etc., for compression and all those things. So whether NDT can be applied, means ultrasonic or maybe X-ray can be used for checking the defects inside, and some decision can be taken.
Yeah, it's a very good question. In fact, we did NDT, but we don't do it on the specimens. We have done it on the sandwich structures with PVC foam and glass epoxy skins. Whether the skin to foam bonding, core bonding is very good. And we did it on small panels, right?
Yeah.
Then we did it on the whole aircraft. One of my colleagues.
Whole component or aircraft.
Whole component, about 200 points we take, critical points. And then we have a standard reference where you have the best bonding. Taking that as a number, we compare with that and put a big plot. And then, well, if within that number, that means the aircraft quality is uniform. And we use what is called coin tap technique, in a mechanized. Earlier, we used to take a 1 rupee coin and tap it, right? If there's a hollow token, then you know that there is a defect. And you can inject the resin and close it. But later we realized that from Japan, we imported some 5-6 lakhs machine. That is, I forgot the name. It is an automatic, it will hit, And then any hollow, it will give a number. That number we put against a standard reference. In fact, one Professor CRL Murthy, a pioneer of NDT.
I know, sir. Yes.
He actually helped us on this.
Lost him recently,
That's right.
Sir, one more point is coming to my mind. You have also mentioned about 3 types of composite materials. One is you have used where that the TG is up to 120 or 150 degrees Celsius. That is you are using for a specific application, for low end application. And other one you are going, that is for bifunctional epoxies, can give you up to 120 degree TG. While multifunctional can go up to 250 degrees, like trifunctional or tetrafunctional. So that they are used for still higher end application where higher TG is required. As you told, that margin should be 120 degrees centigrade.
The higher speed aircraft, yes.
Higher speed aircraft. And the third one was bismaleimide based or cyanoester based. That is the that can go up to even 400 degrees Celsius.
There are PT 30, PT 40.
Yes, sir.
Yeah, 400 variety also there. You are right.
Yeah. So now, in light of that, now what is the latest trend now? Because epoxy resins, though it was called at that time workhorse of engineering. So of course that will include your bifunctional and multifunctional, everything in epoxy family is huge, like ocean of polymer chemistry. Now the thing is, what is now a lot of time has gone after epoxies. Epoxy was very popular during 80s, 90s. But after that, another third have gone. Now, where we are heading to means what is the latest, and whether we are going for bismaleimide, because anyway, we have to increase the longevity as well as the worthiness of the aircraft from various angles, like mechanical properties, thermal, and all those things. So now, what is the latest emerging trend in polymers for aerospace applications?
Well, I think I'll try to answer it with whatever knowledge I have acquired, because I am out of the the field, 2007 to today. But still, I keep always somehow getting some kind of a here and there, and I dig and then get some, Still, they are living on epoxies, one thing.
That's.
Then there are cyanide esters have come up in recent times. I don't know. Some people are trying to make it in the country. I don't know polyamide, but they are trying to make smaller components out of it, like some radomes, for example, which are not very large structures, but they are very expensive. This epoxy which are used in Hansa, special grade. It is a cycloaliphatic, right?
Yes.
Not ordinary epoxy like LY556, etc.
I understand. But cycloaliphatic go up to 180 or 200 degree. I would say the working temperature.
But this, as you said, the cyanide ester and the special case polyamide 30, polyamide 40. That is, it gives 300 and 400 TG, if I understand right. And then, but the thing is, their processing, it is a high temperature processing, number one. Secondly, it is its brittleness and moisture absorption characteristics are to be established the way we have established for the 505 to 556.
Yes, sir.
So I'm sure some work must be going on in my previous department or elsewhere, in DRDO or elsewhere. But one thing is, we have to repeat all those to establish, because the data sheet will give all this. But,
that's true. Yes.
But I'm sure they are the. But one thing, the moment you go to the beauty of epoxy is that it is like a veteran, it a long processing window, right?
Correct.
So today you go to what is called interpenetrating network polymers with epoxy.
I was about to talk about it. Yes, sir.
And one of my colleagues also got a PhD on that. But finally, if you have pure very high temperature polyamide or cyanide ester on one side, the epoxy which cannot exceed say 160 or 180 on the other side, multifunctional. The multifunctional is not one, it is a tri and tetrafunctional mixtures actually. It is a mixed functionalities for the ease of processing and other characters. Therefore, but making pure cyanide ester, they are only for hot engine parts and very small size components.
Understood.
And to make a huge aircraft or something with that is both costly, number two, and cyanide esters are some of these vinyl esters also good at actually quick setting and all. But some of them will be also very the smell and toxicity we have to take care of. That is very important. So on the whole, cyanide esters, people are now looking at it quite a lot. I don't have the first-hand information on that, but that is where I'm telling you, publications are the way to know what is happening. So, what is the publication status,
Correct. Yes.
उसके बारे में ज़्यादा नहीं कह सकता.
Moreover, the moment you think of new, even if this IPNs, in IPNs you are blending the two systems, two resin systems. And they interpenetrate their macromolecular change, they interpenetrate into each other's network. And maybe there may be a partial cross-linking between the two chains also. And
Actually,
of course, that is one alternative for going for the higher characteristics of the final resin.
Yeah, it is
Now
like
the thing is,
a
any resin, if you standardize for a machine like aircraft, which is a huge and so many aspects are involved, including
Yeah.
your moisture absorption, which is more critical.
yes, that is the culprit.
Thing is, yeah. So means any new resin which you are trying on such a huge, I can say the largest system on which it is larger than even a spacecraft, I can tell you.
I see.
The thing is, the complete setup of the testing has to go through. I mean, it's a complete testing. in
Yeah,
all
otherwise,
aspects.
I
It's
tell you,
a huge work.
No, no, as
And
scientists,
establish it like epoxies, because they have taken 50 years to establish epoxy system for aircraft application. Then they are able to run the aircraft from this part of Earth to another.
yes, yes.
So for any other reason they want to change the matrix, then it is I think the repeat of all the testing thing.
That is precisely I'm going to tell you. When you go to certification authorities, whether DGCA or the military airworthiness authority,
yes.
they will ask you all that you please demonstrate it not only on paper but
Yes,
on a
yes.
future level.
Of course, prototypes to be made. Yeah.
So the effort should be a parallel processing as you are tapering out of the conventional materials and go to high performance.
Yeah.
You have to do a lot of in-house research and also make the trial component
The work
demonstrate.
is involved.
Yeah,
Agree.
I'm sure that must be going on now.
Yeah. So thank you very much, sir, for
Thank you, Shuklaji.
clarification and for giving so many answers. Thank you very
Yeah.
much. I just want, because you are available across the platform, so I thought why not to clarify some points.
Sure. We don't have time to otherwise talk,
Actually, sir,
Yeah.
there is no company in India who is making cyanide esters. We are also importing.
Yeah, I know.
There are
this is
some
the
agents who are
quantity
importing and
that-
supplying it us, but there is a
Yeah.
good scope for developing these cyanide esters in the country.
Sir, Adilji, I'll share one thing. As long as we don't develop the material here,
Yeah.
what else we do is only a derivative. We get it. They will tell us how to process it.
Hmm.
So we must now strengthen that fundamental, what I call application-oriented material development programs. Yes. And the space and aeronautics are the best, what I call arenas, where, if you prove them in those sectors, it gets automatically proved in any other sector. For example, I have another suggestion which I've been talking loudly. Hello? So,
Yeah, we are listening, sir.
the fiber metal laminate we have shown, they are flying a 800-seater A380 aircraft, right? My question is, why can't you make automobile bodies with a fiber metal laminate? Has anybody thought about it? A trial car you can make, nothing. It's a beautiful idea, right?
But it will increase to weight and low
No,
efficiency.
No. See, aluminum is 2.8, this is 1.8. Average will be 2.2. It will not be like heavy like aluminum. It will not, but you don't have to make it so, what I call high quality like for the aircraft carrying 800 people, right? See, the beauty of composite is you can tweak that, the formulation development and trial and impact test, everything you can do it.
No, one more doubt comes. You told that in the laminate, if you are in the intervening plies, you are putting aluminum foil, as I understood.
Yeah, that is especially what we call anodized and all that.
Yeah. So when you do the compression of it, compression molding or hot compression of the laminate, final curing, then during this pre-curing process, there won't be diffusion of resin from across the aluminum foil. It is a barrier.
No.
In open laminate, they can
important thing is, sir, I'll tell you, there actually it is a divide and rule principle. If you carefully see that, I told the aluminum is prone to crack.
Okay.
Fiberglass laminates or any composite laminate is prone to delamination because of the layer structure.
Yeah.
So the weaknesses are combined by putting them. The two weak fellows are put together to become a strong. That is the important thing is adhesive epoxy in that glass epoxy will bond together.
It will bond with aluminum also and glass fiber.
Aluminum glass is excellent actually.
Yeah.
It is already established and you have to treat the aluminum and they're all autoclave molded panels, huge panels in big autoclaves.
Okay.
So using maybe 50 or 20 or 30 bars because autoclaves real utility comes in such structures. But using autoclave for everything will make
Yeah.
it too expensive. That is what is called, I told you, appropriate technology, the gypring.
No, an idea comes to my mind. Maybe
Yeah.
you may reject it, sir. Aluminium sheet or aluminium layer or aluminium foil can also be manufactured as a microporous foil because it is used in electro technology, microporous
Yeah.
materials.
You
If
come
that
from
is used,
electricity.
it will allow resin molecules to percolate across it also, and it will become a kind of more compact structure.
No, already they have studied the fact that they have used in a 800-seater aircraft already flying successfully.
Wonderful, wonderful.
The Alcoa is the world leaders in aluminum.
Okay, okay.
The aluminum specialty 604.
Yeah. So I'm sure this idea might have been.
In fact, I have run a program of $10,000 with some Alcoa only before I retired on fiber metal laminates. We did some studies. One of my colleagues is doing it, something. Yeah.
Okay.
So the problem is we fall short of demonstrating and going aggressively improving a material.
No, a lot of work is involved as far as the demonstration comes.
Yeah.
Then plenty
And
of
then
work
later, of
and
course,
study is involved.
that putting it on a large scale, that is another, again, that's a different beyond the scientist capability. That is another.
Yeah, I can understand.
So anyway, sir, thank you for exciting.
Thank you very much, sir, for all explanations. Yes.
So
God bless you.
technology,
It was wonderful.
technology, Rakshita Rakshati, Dharmo Rakshati Rakshati. So thank you to Madhurji and all the participants. I don't know, I've not seen them. I don't know how many people were really able to
There were
access.
13 participants I could see on my screen.
Yeah.
Presently 12. So it is all right. It doesn't matter online. That is the advantage of online. Whether 13 or 130, it is all the same because
this is the working day. One thing I forwarded to some of my colleagues, and some of them acknowledged having seen it. They said they will try to join. But one thing, for those of the people who have worked with me for long, this is just a routine thing because there's nothing more.
Because I understand.
But if it's for those who are really interested in knowing something about the new class of materials, I think this will be a good chance for them.
Right.
And for me also, okay, thank you, sir. But I told you I want to finally thank you all for this and saying the two people have catapulted me into space. One is a booster rocket. The other is what do you call the FOG Perigee motors who have put me in the orbit. But still, I have to make a moon landing now. I think we have landed me on the moon. Thank you.
Sir, there are still 2 questions in the chat box. So I'll read for you. So the question is there any scope for any further improvement for radar radome of LCA, which is successfully developed and certified for airworthiness? The question is from Mr. Jai Kumar Jain.
You are Mr. Jai Kumar?
No, sir. I am Chintamani Pai. So I'm just reading the question.
I didn't get it. Can you repeat it?
Yeah. So I'll read the question again. Is there any scope for any further improvement for radar radome of light combat aircraft, which is successfully developed and certified for airworthiness?
I don't know the status of it, though. When I was in service in 2007, I retired. This LCA radome was talked loudly and is one of my. We regretfully missed that. Otherwise, Jaguar radome we have developed and indigenized and got it certified by Similac, and it is flying on Jaguar maritime aircraft now. And technology transfer also was made from NIL to HIL, right? Who has given us the project? But LCA radome, I think it must be in advanced stage, as I understand. I don't know the status of it at the moment. But the scope for improvement means one is structure, the other electromagnetic, right? So the electromagnetic characterization and certification is a very big task as far as the radomes are concerned. So where they stand and whether they have established, they have frozen everything, whether that is certified, these questions I don't know. If it's certified, nothing like that. We have done a great quantum jump in our radome engineering. Right?
There is one more question, sir. There is question by Nandini Singh. Sir, is there any application of particulate polymer composites in aerospace field, particulate reinforcement in nano size?
Yeah, the aerospace, one thing is, I skipped that particulate composites. Actually, one of my PhD on Bhagyasekar has worked from Josiah College of Engineering. He was my student. And we have worked on the particulate composites, wear and friction, right? By putting in epoxy matrix, metallic copper powder, aluminum powder on one side, then silicon carbide, then graphite, right? And it's a thesis there. It is maybe accessible. Thing is, aircraft applications in the brake pad, they are already used carbon-carbon composites, right? That carbon-carbon means there it is like a carbon matrix. It's not a carbon powder put in the, in something and mold it. It is, you take a carbon-rich like phenol formaldehyde something, and finally through a pyrolytic reaction, and you put that around and liquid and dip your carbon fibers, and then number of pyrolytic cycles, you completely make a carbon fiber in a carbon matrix. It can withstand 2000, 3000 degrees centigrade, right? So the brake pads, but I cannot call it particulate, but as such, particulate composites versus aircraft applications is not very much heard of. I have not heard much about it. So there must be possibilities, yes.
Sir, if we can take one more question.
Carbon nanotubes I already mentioned. See, carbon nanotubes, their length is a few microns and diameter is a nanometer, right? 10 nanometers, 10 to the power -9 like that. Now, they are available as fine powders now. If you see in a powerful electron microscope, you see the length and diameter. But if you take it, it's like a fluffy material. If you put your nose there and then breathe in, it will go into nostril. It is like a aerosol, right? So fine it is. But if you get that carbon nanotube, it's a carbon nano rope, like long fibers. That is fantastic. I think people are trying to do elsewhere. I don't know, it's available open in the market. There is literature, a lot of trials are there. But if you can do it here, nothing like that. Our structures will become very light because the modulus and strength are much higher than even the best of carbon fibers we are using today. Okay.
Sir, if we can take one last question.
Please.
Question is from Mr. Mahadev Lokhande. Question is, can we replace normal helical springs of a given stiffness used in the vibration isolators by springs made up of composite materials?
Sure. In fact, you asked me a very exciting question. I don't know the video, I could have shown it otherwise. See, sometimes accidentally certain things take place, serendipity we call it, right? What we do is when we are doing some resin injection molding for a particular component, the excess waste resin, what we did, we have made it a rod, fine rod, okay? Neat resin casting in a rod form, epoxy, clear, like a glass. Then when it is still soft, hot, I have taken it and wound around a mandrel and let it set. When you took it out, it was looking like a beautiful spring with a lot of strength. If you happen to meet, I can share with you how to make it. And if you put a little reinforcement in that, why not?
Sir, I have seen such a spring which you developed at NAL when I
showed you
those days.
Somewhere in a photo.
Yeah.
I can sometimes share it. See,
it is so making a spring is possible out of glass fiber reinforced plastic and other
but
plastic.
The gentleman who asked me a question, I forget his name. If you can put a little carbon nanotubes in that, it becomes wonderful spring for your automobiles. In fact, this is where I think today we have. I think we can be on email. I don't know. You are working where? Gentleman who asked me, I forget the name. From
Mahadev Lokhande.
He was earlier working in TC. He is retired from there. Mr. Lokhande, he was in TCS.
In?
Tata Consulting Engineering, TCE.
Okay. Right. Okay. In fact, you can use it. You can make a spring, and I can tell you how to make the spring, and you can put any masala in that and make it stiff. And make a trial on some, trucks and small vehicles. Okay, sir. Anything else?
Okay, I think all the questions are over.
Yes, sir.
Yes. So I'm glad that there are at least it invoked some interest in people. And the only regretful thing is I couldn't come on my video. I don't know what went wrong with that. Well, but you have brought
Anyway,
me.
you are enjoying video, sir. Why are you worried?
You are seeing me. I cannot see like I'm a stealthy. No,
No,
मैंने
you are-
stealthy product हो गया.
No, you should. Yeah, I never knew that you are not able, because we can see you very clearly.
No, you
And
can
I'm
see
sure
me.
reciprocally, you must be also watching us.
You are all stealthy and I feel guilty. ठीक है, sir. Madhu ji, and I want to thank you and all your team with your what do you call? I don't get it. ISIE or something. Okay, and your Delhi, Institute of Engineers also participate in this, right? Am I right?
Yes, sir.
So, and I can imagine how much
Institution of Engineers
and
Space
it's
industries.
a great integration of people across the country, and I don't know how many people could have access to it from elsewhere. But thank you very much, and let's be in touch. Maybe next time I'll improve my what do you call this on this how to come online and then operate all.
It's okay. It's okay, sir.
Thank you.
Next
Madhu.
lecture, you will make a lot of practice, and I'm sure that you can use directly from your computer the system.
Yeah.
Maybe.
Yeah.
We'll do
No,
that. Thank you,
some
sir.
small modifications or maybe improvement is required in the system, your desktop itself.
Yes,
It's a minor thing, sir.
minor.
But because it is locked down and nobody is available, no technician you can call also, it is not safe. If one technician comes, who is conversant with the computer systems, for them it may be a matter of 5 minutes to correct the system.
Yes.
That is the only hurdle. Doesn't matter.
It's okay. We'll wait.
Yeah,
let's
till
hope
normal
things-
time comes. Yes, it can be done, sir.
Yeah, we'll do that and
Minor
take
things, sir.
care.
Yes.
Thank you both,
Including
and
mobile.
all the people who asked me
Thank you
questions.
very much.
And I told
Yeah.
you, they
Okay.
can always access me on my email.
Oh,
And
certainly.
to the extent possible, I'll try to answer the questions. Any
Right.
doubts?
Yeah.
Thank you, sir. Madhuji, take care. And
Thank
take
you very
care.
much, sir, for sparing your time.
No, no.
Very
it was
nice
like a-
lecture.
Actually, you have activated me. I was just
Oh.
deep slumber.
So,
Thank you. Bye.
I am trying to catch all retired, experienced people. They have got good khajana with them.
Some people said I'm retired but not tired.
Yes, definitely.
And I'm retreaded now.
Yeah.
Thank you.
Okay, go ahead, Chintamani.
Bye. I'm switching off now, leaving. And I
No,
must
no.
leave.
Sir, wait a minute. Now, Chintamani will wind up. 2
Thank
minutes.
you very much, sir, once again for enlightening us on the world of composite materials. And I'm sure all of us who were listening to your talk, they enjoyed this talk and they were revitalized to
Yeah, thank you.
work in the field of composite materials. Unfortunately, the next speaker is not available due to some personal problems. So we are not having the next session. So actually we are going to stop here. And before we stop here, again, we are up for the day 4. And day 4 again starts with beautiful talks on basically drones and
Robotics, robot.
Axis development in India and the role of robotics and automation in growth of various sectors.
Oh, that's a very high science and high. Now I'll try to join. We'll see. And just if we can learn something from. And today I saw one IIT Kharagpur professor on micro machining. Yeah, that's interesting.
So we look forward to seeing you all on day 4. And till then, goodbye.
Sure.
Thank you.
Your good name I didn't register.
Sir, he is Mr. Chintamani Pai. He is running a NGO in Bombay.
Yeah, I see his name very often. So, जब चिंतामणि साहब बाहर आएंगे, मैं चिंता नहीं करेंगे.
No chinta, only money.
Yes. No.
Sir,
Sir, in our programs, we are having no chinta because of him, but money also we are not getting. That part is lagging.
Yeah.
Because we are
That's
doing
true.
all activities most of the time free of charge. We are charging
Yeah,
very minimum amount from it.
Yes, yes.
That's possible. Thank you.
Thank you
Thank
very
you.
much.
And I am also beneficiaries. Thank you.
Thank you, sir.
Bye bye, sir.
Bye.
I'm
Thank you.
leaving now.
Yes, we'll leave.
Okay, bye.
Okay, bye-bye.
Yes, sir.